Yeah. Yeah. Good evening. Thanks all for showing up. I think this will be a lot of fun. So yeah, I'm Andrew Moore. In case anyone didn't know, I'm a forecaster at the Storm Prediction Center along with Andrew Lyons. And so we both came through school here at OU, both went off to winter weather offices, and both had a steep learning curve because let's face it, OU doesn't really focus on winter weather, we focus on severe weather. And so, at least for my talk here, this is going to be like a quick rundown of everything that I had to learn on the job when I got out of school and had to go into the weather service. So, just a quick little background. I went off to the WFO Grand Forks, North Dakota, which is right on the border with North Dakota and Minnesota. For those that might not be familiar, we're going to talk a lot about that region because I have a lot of examples from this area. So in this workshop tonight, we're going to kind of break it down into 4 topics plus a forecast challenge. That should be an exclamation point because we ended up making a really fun one. So my 2 sections are going to focus on heavy snow and blizzards, and then Andrew Lyons will handle snow squalls and freezing rain, mixed precipitation type, and that fun stuff. So yeah, the first part, we're going to focus on heavy snow. Just a quick little caveat. I should have put a little star over heavy snow because heavy snow can mean different things to different people, depending on where you're at in the country. So for example, here in Oklahoma, if we get 3 inches of snow, that's climatologically pretty anomalous. Like we just don't get that much snow that often. If you're in North Dakota or in the mountains out west, 3 inches of snow is just another Monday. Like no one would blink an eye at that. So it's kind of there's a caveat there. Also, whenever we refer to heavy snow, you have to ask yourself, okay, are we referring to snow rates? Because oftentimes we'll talk about snow rates. Are we talking about 1 inch per hour, 2 inch per hour? Are we talking about visibility reductions down to a quarter mile or less because of falling snow? It gets really complicated really quick because then you get into like snow crystals, and the type of snow crystal can change the visibility from the sensors on the ASOSs and AWOSs, and it gets really complicated really quick. So whenever I refer to heavy snow, I'm just going to more broadly talk about swaths of 4 inches or more, because that's typically what we refer to here as heavy snow. But just know that if you go to different places across the country, it might change in definition. So for a synoptic pattern, in general, we're going to cover the big synoptic patterns. And again, this is going to be a skimming the surface of winter weather forecasting. There's probably going to be some topics for our winter weather buffs that you're like, hey, why didn't you cover this topic? That's because there's a lot. We could spend hours upon hours talking about winter weather alone. So we're just going to kind of skim the surface, look at the big picture, tools that you can use walking out of here tonight and start trying to forecast heavy snow. So we're going to start with the synoptic pattern. So this should look pretty familiar, typical Norwegian cyclone model. We've got a low pressure area. We've got our warm front to the east, northeast, the cold front down to the south, southwest. And typically what we're going to look for is on the backside of the low, we have what's called the cold conveyor belt. So you might be familiar with this area, but really all it is just a swath of cold air wrapping from the north side of the low down around the west side of the low. We also have something called the warm conveyor belt. Now, this is air that's originating out in the warm sector from the southeast quadrant of the low. It's coming up towards the north, and it actually branches off. So right here, I actually have it branching off to the west, going to the north of the low. There's also a branch that branches off to the east, but that eastern branch isn't nearly as interesting. So we really just focus on the western branch, and we're going to focus on that a little bit more in just a bit. And then typically we'll have some kind of strong mid-level jet coming in. And we're going to talk about the dynamics of why that mid-level jet is so important and why we look for it when we're trying to forecast heavy snow. So typically, whenever we have our typical Norwegian surface model with a surface cyclone, what we'll tend to see is we'll have this swath of light to moderate snow on the northwest side of our surface low track with an embedded swath of heavier snow. And it's this embedded swath that's typically where you're going to see your heavier snowfall rates, 1 to 2 inch per hour snowfall rates, heavier amounts above 4 to 6 inches. And there's kind of a caveat here as well. So in general, meteorologists are really good at predicting where this swath of light to moderate snowfall is going to set up, because generally speaking, deterministic models, are really good at getting the low track. But what they're not great at is getting the location of where this heavier snowfall swath is going to end up. And the way that I like to think about it, and the way that we communicated it at Grand Forks, was you think about it like summertime thunderstorms. So you have a general area where it's like, yeah, we have a pretty good idea there's going to be thunderstorms in this vicinity, but we don't know exactly where these thunderstorms are going to set up. It's the same thing here. We have a general idea of like, yeah, there's going to be a swath of light to moderate snow. Somewhere in that swath, we're going to see a heavier band. We might not know where it's going to set up until we start to see it on radar. but we know it's going to end up somewhere in this region. And this is what the snowfall totals will look like. So this is from a real event. So the surface low, if you're following this model, is somewhere down here towards the Twin Cities. So this is eastern North Dakota, northwest Minnesota here. Grand Forks is right there at that 6 to 8 gradient. But check out this swath of 12 to 18 inches, all the way, 6+ inches, all the way towards Lake of the Woods, which is this little lake right here. So we had a nice swath of snow. So this is really stereotypical of what we see in the Dakotas, really anywhere east of the Rockies. But notice that we have a much broader area of light to moderate snow with that heavier swath embedded within there. And this is what that should look like on radar. So as this loop goes through, watch where this green line is. You're going to start to see the darker blue start to consolidate around that green line. And this is an example of a heavy snow band that will result in this heavy snow swath. So right there, you can start to see it consolidating right through here from west of Grand Forks to the west of the Fargo area. There it is. So this is an example of that heavy snow band that sets up and starts to just really dump those heavy snowfall rates, giving you the 12 to 18 inches of snow. All right, so I'm going to keep on going for the sake of time. So that's the general synoptic overview of what we're looking for, but how do we try to anticipate that? Well, this is what we're going to try to look for. We're going to look for a favorable overlap of synoptic scale ascent. So think broad picture, upper level troughs, upper level jets, but also mesoscale ascent. So mid-level frontogenesis, mid-level warm air advection, and deformation zones. We're also going to try to look for ascent within the dendritic growth zone. And I think I've kind of mentioned this already, but I'm going to toss in the caveat that this talk will primarily focus on the plains and east of the Rockies. So these concepts are good for the Northeast, the Southeast, the Southern Plains, Northern Plains. Once you toss in mountains, that's a different story. And that's where Mr. Lyons' expertise comes in, because he was actually in the mountains. I was in the very, very flat plains of North Dakota. All right, so let's say, for example, that we have a 500 millibar height field that looks something like this. So we have, our upper level trough that's surrounded by 2 ridges, and we have some kind of vorticity maximum right here. So if you're in your senior level class, you're probably familiar with QG dynamics, and you might be able to explain why we pay attention to the vorticity maxima and where they're going to go, because that can tell you where we might have broad scale ascent. The thing to know for right now is that wherever we have these upper level troughs, just pay attention to where they're moving to, because just ahead of those upper level troughs, that's typically where we see broad scale ascent. So we're thinking, weak ascent in general, maybe centimeters per hour, but it's over a much broad, very broad area. All right, and this is just highlighting that region of broad but weak ascent. All right, now let's say that we have some kind of a jet streak. So this is a really quick primer on jet streak dynamics. So right here we have some kind of jet streak. In the middle of it, in the core, we have 100-knot winds surrounded by a swath of 75 and 50-knot winds. And let's say that we have some kind of air parcel. He's over here. He's going to come into this jet streak, and we're going to see how the forces are going to move this parcel around. So according to QG theory, you're basically going to assume that all the parcels in the upper levels of the atmosphere are balanced between Coriolis and pressure gradient force. And so those 2 forces are going to keep it balanced. And anytime it gets out of balance, those parcels are going to accelerate in directions where they don't really want to go. And that's going to cause areas of difluence aloft and confluence, which results in vertical motion. So let's take our little imaginary parcel, and he's going to go into the jet streak. So he's entering the jet streak, and as he gets there, the pressure gradient force, so keep in mind that the winds are correlated with the pressure gradient force. The stronger your pressure gradient force, the stronger your winds. So you can infer that as this parcel enters the jet streak, the pressure gradient force increases and pushes that force balance out of whack. It's going to push the parcel off towards the north. Now it enters into the core of the jet streak. By this point, the Coriolis has had some time to respond. And so those forces come back into balance as that parcel is entering the core of the jet streak. Now it's starting to exit. So now we're in the exit region. And again, these balances are going to get out of whack. The Coriolis force is still the same magnitude as it was when it was in the center of the jet streak. So it's really strong, but the pressure gradient force is weakening very quickly. So this causes a imbalance in these forces, but now the Coriolis is going to be throwing this parcel into a direction it doesn't really want to go. And then finally, our particle exits the jet streak, the forces come back into balance, and it just goes on its merry way. But what this path does is it creates areas of convergence and divergence aloft. So in the left entrance region, yeah, I had to like remind myself which is which. Yeah, in the left entrance region, we're actually going to see convergence, net convergence, with net divergence in the right entrance region. And we're going to see the opposite in the exit region. So in the exit region, we have net divergence to the north and net convergence to the south. Now keep in mind, mass continuity says that if you have an incompressible fluid, which we assume the atmosphere is under synoptic conditions, if it's incompressible and you're shoving mass together, that mass has to go somewhere. And so it either has to go up or down. But we're already kind of towards the top of the atmosphere. Some of it will go up, but a lot of it's going to go down as well. So if you're pushing mass together, you're going to have some kind of vertical motion response, and this gives us vertical ascent within the atmosphere. So the things that we're going to watch for is to see where do we get divergence aloft, because these are our areas of ascent. Typically, let me move this real quick. Perfect. So typically in a zonal jet streak, which is what we see most of the time, the left exit region is causing ascent in the colder air. So when we're forecasting for heavy snow, we want to see where do we get the strongest ascent in the coldest air. That's typically going to be in the left exit region. Oop. There we go. Whoop. Okay, here we go. Sorry about that. All right, so let's put this into context with our upper level trough. So we have the same upper level trough as before, but now we've added this jet streak here. So if you recall, out ahead of the upper level trough, we had broad, weak ascent. But now we introduce this jet streak, and we introduce the left exit region. So this is going to tell us where our strongest synoptic scale ascent is going to be. It's going to be just ahead of the trough and in the left exit region of that jet streak. So this is the area where we want to see we're going to start to set up the potential for heavy snowfall. All right, so mesoscale ascent. The first one we're going to focus on is phronogenesis. All this is strengthening a temperature gradient at some level. So phronogenesis can get really confusing with the math. But just keep in mind, every time you hear phronogenesis, just think strengthening a temperature gradient at some level. That's all it is. So let's see some examples of this. So let's say that at time one, we have a temperature gradient that looks kind of like this. And notice that we have confluence. So the wind is going to push these isotherms together with time. And so by the time we get to time two over here, our gradient has actually strengthened because those isotherms are coming closer together. All right, here's another example. In this case, we actually don't have phronogenesis. Notice that our winds are parallel to our isotherms. So there's no temperature advection at all. The wind is not pushing our isotherms closer together. And so going from time one to time two, we actually don't see any change. So there's no phronogenesis happening in this case. And in this case, we actually have the opposite. We have frontalysis, which is just the weakening of a temperature gradient. So in this case, our winds are actually pulling our isotherms apart. That's going to cause this temperature gradient to spread out, become more diffuse. And with time, we actually get a weakening temperature gradient. But it's not just horizontal. So the last three examples were all horizontal temperature gradients, but you can have vertical temperature gradients as well. So here's an example. Over here, we have time one. So here's the ground in the brown. And let's say we have some kind of vertical motion. Let's say we're in the left exit region of a jet streak. So we have vertical motion through a layer. And this is how our temperature profile looks. With time, this vertical motion is actually going to compress that temperature gradient, push those isotherms together, and strengthen the front, essentially. All right, so why do we care about this? The reason we care about phronogenesis is that whenever you're strengthening a temperature gradient, you're basically increasing, well, let me rephrase that sentence. The atmosphere wants to destroy temperature gradients. It wants to maintain equilibrium in itself, which means that you have all your isotherm, or all your wind is flowing parallel to your isotherms. You have no baroclinicity. And so whenever you're generating a temperature gradient, you're throwing the atmosphere out of equilibrium. And so in order to get back to equilibrium, we have what we call the phronogenetical response. And essentially, this is just a vertical circulation that occurs to try to spread that temperature gradient back out. So anytime you're bringing isotherms together, the atmosphere is going to try its best to spread them back out. But what this does is it causes ascent on the warm side of the boundary. And so this is a good example of this here, where we start to build our temperature gradient. And so this is like a cross section looking in the X and Z directions. We're going to see ascent on the warm side of that boundary. And this can give us extra mesoscale ascent and help aid in precipitation. So here's another example. So I can't recall off the top of my head which stations these are. Lyons, do you remember which?
Cedar Rapids. No idea. Yes.
Yeah, I have no idea either.
Somewhere in Iowa, I think. Maybe. That's actually pretty close to Iowa. Never mind. I have no idea what that is.
Yeah, we should know better. We're not good at geography. It's all good. But this actually is a good illustration. So what we're seeing here is actually an isotropic analysis. If you're not familiar with isotropes and what they are, don't worry too much about that. Just think of them as isotherms for all intents and purposes right now. But what this cross-section is showing that phrenogenetical circulation, that phrenogenetical response. So right through here, we have a tight packing of the isotherms. And so you can see that we also have vertical motion through this layer as a result of that tight packing of the isotherms, which is causing ascent, which can, if it's overlapped with broad synoptic ascent, really enhance your vertical motion, really enhance your precipitation rate.
It's Farmville, Virginia. I thought it was.
Oh, FVX?
No, I'm embarrassed. That is Shatter, Nebraska. That was in my old honeymoon. I should know that. It's like shame on me. But that is a cross section across the entire country.
Oh, perfect. There you go.
Thank you.
All right, so that's phrenogenesis, and we're gonna see some examples of this in just a bit. We're gonna quickly talk about warm air advection. So again, if you're familiar with QG theory, you know that warm air advection is basically synonymous with ascent. If you're not familiar with QG theory, just take it on faith that warm air advection is synonymous with ascent. Essentially what you're doing, so you can imagine that this is an isotherm here. Really, it's an isentrope, and parcels like to stay on their isentrope. Again, if you're not familiar with it, that's quite all right. Just take it on faith for now. But essentially what happens in a warm frontal zone, is that a parcel will enter the warm frontal zone and then be lifted along it instead of passing straight through it. And that ascent can actually, again, be very strongly focused, and when it's overlapped with proper synoptic ascent, can enhance precipitation rates. All right, so just to touch on warm air advection a little bit more, I talked about the warm conveyor belt earlier on and how we actually care about the westward branch of it. So this is a really good schematic showing those two branches. So what we're seeing here, here's our surface low back over here, our cold front. This one's actually occluded. You can see the occluded front in there. Here's our warm front, and here's the warm conveyor belt. So it's starting down here at 900 millibars. It goes up to 850, 800, and then at about 800, 700 millibars, it actually splits off. And so we see it at 650, it's splitting off to the west and off to the east, and it's ascending as it goes. So by the time it gets back towards our surface low, to the north of the surface low, it's at around 550 millibars. So essentially what this is a branch of warm air advection that's wrapping back behind the surface low. And so what's going to happen is that this warm air advection is going to focus mesoscale ascent, which can then overlap with our synoptic ascent and result in our heavy snowfall rates. Sometimes you're probably going to hear this referred to as a trough of warm air aloft. That's just a fancy phrase for saying warm air advection on the north side of the surface low in the mid levels, mid to upper levels. So anytime you hear trowel, just think warm air advection in the mid levels to the north of the surface low.
Be careful when you say that acronym. People get really fired up about that. So.
Passions run very high about acronyms.
Yeah.
Oh, there it is. So here's an example of this from a real satellite image. And this is a really great example. So obviously here's our synoptic low. It's wrapping around. We have a dry conveyor belt with this dry slot wrapping all the way back around to the north, northwest of the low. But here's our warm conveyor belt. And you can see this depicted by all the cloud cover. We have a warm conveyor belt. Part of it branches off to the east, but part of it wraps all the way back around towards Nebraska, almost into Iowa. So all through here, you're getting warm air advection in the mid to upper levels of the atmosphere. So you wouldn't typically see it at the surface like where you'd expect to see a warm front. We're seeing it much higher up. And all through here, you can expect augmented precipitation rates because of that ascent associated with the warm air advection. All right, so the last focused or mesoscale ascent thing that we're going to focus on is deformation zones. Simply put, deformation zones can be thought of as regions of convergence in the atmosphere. You can see them at all kinds of levels. You can see them at the surface, aloft, mid-levels. Typically, when we're thinking about heavy snow, we're going to be looking in the mid-levels. Personally, I like to look for them at 850 or 700 millibars. Really, at 700 millibars, that's where it really comes in handy. But again, due to mass continuity, anytime you're smushing mass together, you have to have some kind of vertical motion in response. And so where you get this deformation zone, you can actually enhance precipitation rates. But there's also another effect here. So here's a weird pseudo cross-section of a deformation zone. So the black arrows are the horizontal winds coming together. Green arrows are the vertical motion. Red are the downward motion. And let's say that we have a snow shower in this deformation zone. Well, what this is going to do is actually elongate that snow shower along the axis of dilatation, I think. Yeah, dilatation. And basically what's going to do is it's going to prolong the precipitation rates over the same region. And so just imagine you have, it's kind of like almost akin to a flash flooding event where you have a rain shower or a snow shower that basically just stays in the same region for a prolonged amount of time. And so maybe a few hours later, this is what that zone of ascent looks like. You're just elongating it and extending the duration that it can stay over one area. And this is how you get, or helps get, the crazy snowfall amounts. So here's an example of a deformation zone. This one's actually 850. So notice that over Oklahoma and Kansas, we have southwest winds about 25, 30 knots. Once you get into Iowa, they kind of branch off. Over here, it becomes more to the out of the southeast. Over here, it's more out of the northwest. And if we look into the Great Lakes into Wisconsin, we actually have northerly winds. So you can see how we have that mass response coming together, and then along the axis of dilatation where they're spreading out, you're getting flow going in the opposite direction. So imagine if you had a precipitation band right here, it's going to elongate in that northwest to southeast direction and can remain over that region for several hours. There it is. So here's another example. Excuse me. So this one's at 700 millibars. Like I said, this is personally where I go to look for them first. Notice, so here's our synoptic low at 700 millibars. We have southwest becoming southerly flow out ahead of it. And then we have this warm frontal zone in through here. But notice back to the northwest, we have northerly winds coming down out of Minnesota, Iowa, and into Missouri. And in between this is where our deformation zone is. Again, we have confluence coming together and then an axis where it's spreading out apart. And so it's right through here in this axis. That's where we would expect potentially some prolonged precipitation. Okay, so pop quiz, moving on to snowflakes. Which of the following snowflake shapes is going to be the least efficient at compacting? So who would say it's A, columns and plates? These are going to be the least efficient at compacting on the ground. All right, anybody say needles? All right, we got some needles. Anybody say dendrites? All right, I think the dendrites have it, and the dendrites are correct. So this kind of comes down to, this is one of the nuances, again, of winter weather forecasting and snow measuring. So let's say, for example, that you have, let's take the same amount of QPF or QPE rainfall amounts, let's say 1 inch of rain. And let's say that this rain is going to fall as snow, but it can only fall as columns and plates. Basically, once all those columns and plates hit the ground, they're going to be able to compact much faster and much easier than needles or dendrites. And so even though you have the same amount of rainfall, when it's as snow, it might only seem like 1/10 of an inch. It might seem like pretty minimal snowfall. But now let's say we have all dendrites, and these dendrites like to clump together. So if you were watching the snowfall yesterday, we had some massive aggregates of dendrites that were clumping together and falling as one massive snowflake. Dendrites aren't as good as compacting. In fact, what's really fun to do is if you take a time lapse of a snowpack after a big snowfall with dendrites, you will actually start to see it compact and sink down over time. That's because it takes time for the dendrites to break up and melt, and then they start to compact. So if you get a snowfall with mostly dendrites, you can actually see higher snowfall amounts measuring with a ruler than you can with columns and plates or with needles. So if we want heavy snowfall, we need to maximize our dendrite production. And that's all that's saying right there. All right, so what temperature range is going to be best for producing dendrites? That's the next obvious question. So we're going to introduce something called the dendritic growth zone, which is roughly between -12 Celsius to -17 Celsius. Sometimes you'll see this being called from -10 to -20. For all intents and purposes, that's close enough. Just know that it's somewhere in that range. That's where we can maximize the production of our dendrites. All right, so this is how we find this on a SQT. So all you have to do is go down here, find -12 and -17, and I've highlighted them in the blue lines, and go up and see where does our temperature profile intersect those two isotherms, and how deep is that layer? So for example, this DGZ is from, I think, my bad. That's in feet, so that's 13,673 feet to about 17,000 feet. So about 3.5 kilometers deep. I'm sorry, 3,500 feet deep. That's not bad. That's normal for a dendritic growth zone. Generally speaking, the deeper you have it, the better. The more saturated it is, the better. And this is the key. The more ascent that we have within that layer, the better, because we're tossing up a lot of mass within the area where we can best produce dendrites.
Real quick on that one.
Oh, yeah.
So you guys remember from the sounding stuff, right? When the red and green line on the sounding are next to each other, that indicates saturation, right? That's 100% relative humidity. Is that profile saturated? Say up through 300 milliwatt? No. Are you sure? Yeah. It actually is. So relative humidity with respect to ice is different than relative humidity with respect to water. So whoever said it was not saturated, it is saturated, you were correct, because ice is actually slightly easier to get saturation. So those lines don't actually have to touch to be saturated with respect to ice.
Yeah, that's a great point. And that's one of those little nuances that it's really easy to forget, but very important. All right, so let's see some other dendritic growth zones. So here's a really deep one. This one extends from roughly, I'm just going to call it 750 millibars up to above 550 millibars. This one is pretty deep and it's mostly saturated. So if we had a lot of ascent between 750 to 550, this would be a pretty good profile for generating heavy snow. Let's see another one. So this one's a little bit more shallow. It's not quite as saturated. It's still close to saturation. If you got enough ascent in there, you could probably saturate it. But this is kind of on the shallower side. This would just kind of give you a so-so snowfall rates. So this is something that we pay attention to whenever we're doing our MCDs for winter weather. We see, okay, how deep is the dendritic growth zone? If it's really deep and we have a lot of ascent within that layer, awesome. If not, maybe it's not a great setup. Okay, so just a quick recap. How do we forecast the heavier bands? We look for favorable overlap of synoptic ascent, mesoscale ascent, and we try to maximize ascent within the dendritic growth zone. So for example, let's say we have a warm front at 700 millibars. We have warm air advection at 700 millibars, and our dendritic growth zone goes through 700 millibars as well. That's a great setup. That means you have ascent within your dendritic growth zone, and you can expect potentially heavier snowfall rates. And I made this little note here that, and this is the way it really has to be thought about, is that the probability of a heavy snow band developing increases the more and more that these factors are overlapped or aligned spatially and temporally. So if one of these factors is a little bit off, that might be okay if the other two can compensate for it. If you get all three, then your probability of a heavy snowfall band is going to go up. So you always have to kind of think probabilistically. Do I have all three, or maybe just a combination of one or more of them? All right, but let's start looking at some examples, and then we'll hop into blizzards real quick. Excuse me. So this is a 300 millibar height map. And so we're going to be looking for upper level jets in this case. So there's a couple here. There's this one coming across the four corners, but there's a much stronger upper jet right here going from Iowa into Minnesota. So we're going to focus on this one primarily. Oh, and here's our upper level trough. So I mentioned earlier that we look for a broad scale ascent ahead of our upper level troughs. Right here is our trough axis. So anywhere northeast of this line, so all the way from Oklahoma up to the Dakotas, we can expect broad scale but weak synoptic ascent. And now let's focus on the jet streak, and we're going to divide it into our four quadrants. So we're going to look at the left exit, and the left entrance and right entrance regions, the left exit, right exit regions. And as we mentioned, typically speaking, we see the strongest ascent over the colder air in the left exit region. So we're going to focus on this quadrant right up here. Okay, so right now we have this green box, and we'll just stop and think about this for just a second. So in this green box, we have the left exit region, jet streak dynamics. Awesome, cool. And we have broad scale ascent ahead of the approaching upper level trough. So right there, we have our synoptic ascent. So now we need to take a step down in the atmosphere and start looking for mesoscale ascent that might fall within this green box. All right, so this is the same thing at 500 millibars, just pointing out that we still have some favorable synoptic ascent at 500, at the southern end of this green box. Also notice, this is a heavy snow case, but there's a hurricane about to hit Alabama. So yeah, this was early October 2018. I worked this case. It was a lot of fun, actually. Okay, so let's jump down. This is going to be 700 millibars. And notice what we have right through here. We have a really strong packing of the isotherms. We have southwesterly winds at about 45 knots. Up here, we have northeast winds at 15 to 20 knots. And we have a warm front positioned right through here. Really, this warm front goes, here's our 700 millibar low across eastern South Dakota. That warm front extends all the way into Minnesota and into southern Canada. So anywhere through here, we actually have pretty strong mesoscale ascent. I primarily focus on the warm front, but also notice there's a deformation zone here that's co-located with that warm front because we have the northerly winds here, southerly winds down here. So we have to have some kind of mass response in between to compensate for mass continuity. And so here I highlighted in this purple box that this is where we're getting the best overlap of our synoptic ascent and our mesoscale ascent. All right, so let's hop down to 850 millibars. Now we start to see that, okay, our warm front, as expected, it's a little bit further south than the 700 millibar warm front. That's pretty typical. Warm fronts typically slope up to the north with height. But we're still potentially getting, some influence from the 850 millibar warm front. It's just slightly displaced. So it seems like, at least in this case, we're going to be looking at 700 millibars and above for our stronger synoptic and mesoscale ascent. This is the 850 warm air advection, or temperature advection, sorry. So you can really see where the cold front is, where that really strong warm front is. And notice that we do get some overlap right through here with our green and purple boxes. So maybe we'll see slightly heavier snowfall down here. That could be one implication of it. And here's frontogenesis. So this is actually looking from 850 to 700 millibars. I would always encourage you to look at a deep layer for frontogenesis instead of just at one single layer. Because what we often see is that frontogenesis may be weak at 850, but really strong, from like 825 above. And so this is just one trick of the trade. We always try to look in between layers to get an idea of how strong frontogenesis is. And in this case, it's really strong just north of the Great Lakes. That's about as strong as you'll see it get. But we do have some frontogenesis extending back into northwest Minnesota and eastern North Dakota. So again, we see where do we have favorable overlap with the green box being our synoptic ascent, the purple box being our mesoscale ascent. It's all kind of focusing in eastern North Dakota, northwest Minnesota. So here's surface pressure. There's our hurricane. Yeah, so everyone's focused on the hurricane, whatever. We're getting snow in North Dakota, and we're like, we're more important than that. Come on, let's go. Yeah, it was fun. But just to show that, this still fits in with our Norwegian model. Notice that our surface low is right here, southern Minnesota, northern Iowa, and where we're expecting a potentially heavy snowfall band to set up is going to be off to the northwest, right over here. This is actually a good blizzard setup, and we're going to talk about that a little bit more in a bit. And here, it looks miserable.
That looks miserable.
It was fun. It's fun. So here is near surface freezing wet bulb temperatures. Just gives you an idea of, is it freezing near the surface, yes or no? The purple line denotes freezing. So you can see that right through here, we actually have a little bit of cold air advection. Here's our freezing line. So maybe in Minnesota, we might have some precipitation type problems. It looks like it's warm at the surface. So maybe it could fall as primarily rain. But eastern North Dakota, we're below freezing. So maybe that's where we should focus our messaging and our forecast for heavy snow. And I apologize, I couldn't find really good composite radar imagery. But this is what the radar looked like just a few hours later from those plots. And this was the onset of the event when we actually started to see our heavy snow band develop across eastern North Dakota. And you can see the higher reflectivities setting up from far northwest Minnesota down to about just west of Fargo. There we go. And a few hours later, that snow band continued. It persisted for several hours and basically just sat over eastern North Dakota because the surface low was starting to occlude, so it slowed down. And just, again, that deformation zone helped prolong the duration of snowfall in the same region. And it's not really shown here because we don't have the Canadian radars in this composite, but this snow band actually extended well into southern Canada as well. And I kind of gave a precursor. This was actually the same event that we just looked at. This is how we ended up getting that 12 to 18 inches from, just west of Fargo all the way up into Lake of the Woods, far northern Minnesota. And like I said here, the heavy snow extended well into Canada. So this was a pretty big snowfall event for us. So this was my first winter up there. It was a lot of fun to go through this, especially being from Arkansas and Oklahoma, where this kind of snow just doesn't happen. So just a quick recap. Again, we're looking for that favorable overlap of synoptic ascent, the mesoscale ascent, and ascent within the dendroid growth zone, which I apologize, I couldn't find a great sounding for that case because Grand Forks doesn't have a sounding. So that's kind of tough. But really quick, so we got about 15, 20 minutes. We're going to touch on blizzards real quick, which are going to be very, very similar to heavy snowfall scenarios, just with one added component, and that's the wind. So what constitutes a blizzard? Go to the Northern Plains and ask a forecaster what constitutes a blizzard, and you might be there for several hours. Some of them are very bitter because back in the day, so I'll start with the definition. So whenever we say the word blizzard, what we're referring to is heavy snowfall and or really strong blowing snow. We're also looking for reduced visibility down to a quarter mile during the daytime, half a mile during the nighttime. This is one of those weird nuances about snow visibilities. We can get into it if you have questions in a bit. Just take that on faith. That's what we look for. And then the big one is sustained winds of 35 miles per hour or greater. You will see some people argue that it's not sustained winds, it's wind gusts above 35 miles per hour. I would argue, no, that is not a blizzard. That is a strong snowstorm. But for a true blizzard, I would argue, you need sustained winds of 35 miles per hour or greater. And all these conditions have to be maintained for 3 hours straight. So you can't have 1 hour of these conditions, take a break, another hour. That's not really quite a blizzard. You need it for 3 solid hours. So back in the day, this is where all the old timer forecasters get kind of angry and shout at you. Back in the day, there used to be a fourth component to this, where it was temperature. You had to have wind chills below a certain temperature, and I forget what the threshold was, but it was something crazy cold. And the argument was that whenever people get into blizzards, say you're driving down the interstate, it's whiteout conditions, you can't see, you run into a snowdrift, you're stranded. Chances are you're going to survive. As long as you have some equipment in your car, you're going to be okay. The killer in the blizzards is the wind chill, because people are panicked. Oh no, I'm stuck in my car. I need to get out, try to walk to the next town. It's only a mile away. They get disoriented, and then the wind chill is what ends up killing them. If anyone's heard of the children's blizzard, I forgot when it was, around the turn of the century. It was a blizzard in South Dakota, eastern South Dakota, that killed like scores of people. They call it the children's blizzard because a group of school children got caught in it, and unfortunately a lot of them perished. So
12, 1888.
there you go. Thank you for that. I knew it was in the 1800s. I couldn't remember when. But yeah, so that's just kind of keep that caveat in mind. Some people argue you need the wind chill component. Today, we don't typically have that threshold of that criteria. Okay, so where do blizzards occur? They are most common across the Dakotas, really, and specifically through the Red River Valley of the North, which the Red River of the North runs from roughly western Minnesota into far northeast South Dakota, and then right along the Minnesota-North Dakota border. It basically is the border, and into basically all the way to Winnipeg, and then it goes into Hudson Bay. So this area is like really fascinating because it's basically as flat as this table, but there's just enough slope to the river valley to funnel winds and create some fantastic blizzards in this very localized corridor, which you see in this paper. So this is from Coleman and Schwartz, 2017. And they were just seeing like, where do blizzards most frequently occur? Well, it's mostly in the plains. or northern plains, and specifically through the Red River Valley. If anyone wants a really fun office to go work at, I encourage you to go work at Grand Forks because the blizzards are a lot of fun. But notice that we can get blizzards basically anywhere. Oklahoma's here. If you go talk to some SPC forecasters, they were here during the last really big blizzard in Norman, and they will tell you stories about it. Andrew Lyons and I have heard many stories about it, many times.
Same story, repeated all the time.
Yep. So it can happen. It can happen anywhere, except for maybe far southern, lower Mississippi Valley, and perhaps over the desert of the Southwest, just because it's so dry out there. It's really tough to get the snow. But basically, anywhere else is fair game. So I would argue that there are two types of blizzards. You have your typical blizzard, which features heavy snowfall, the winds, the blowing snow, and then we have ground blizzards, where you can get blizzard conditions, but you don't have any falling snow. You could have clear skies and still have a blizzard ongoing. And these are really cool. We're going to show some really cool imagery from this. But first, let's focus on the standard blizzards. So this is going to look familiar. In order to get the heavy snowfall for our blizzard, we're going to follow the same recipe that we did for our heavy snowfall forecasting. So we look for a strong synoptic low, upper level trough moving in, surface low deepening, jet stream coming out. We're going to look for the favorable overlap of synoptic ascent, mesoscale ascent, good ascent within the dendritic growth zone. And we'll get our band of moderate to heavy snowfall. But then this is kind of the key difference. We need a surface high to be strengthening at the same time that our low is deepening. This typically happens when you have really cold air intrusions from the central plains of Canada plunging down into the central plains of the US. That's typically when we see the strongest surface surface high pressures building. And this results in really strong pressure gradient winds, which then can sustain our 35-mile-per-hour winds across a really broad area. And so this is kind of a little bonus and something that we pay attention to, at least at Grand Forks. This was kind of a make or break for a lot of blizzard scenarios. We look for really strong cold advection just above the ground. And so I'm going to take a quick second to kind of focus on this because it's a little bit nuanced. And it's not what you might expect in this kind of environment. So let's say that we have a sounding from the southern end of our heavy snowfall band. And this is what our temperature dew point pressure looks like. Now let's say just above the surface, let's say 925, 900 millibars, somewhere in that vicinity, we have a level of max cold air advection. So essentially what's happening is that our profile is being shoved off to the left of our diagram, much faster than the surface temperatures are cooling off. And what this results in is a layer of nearly dry adiabatic lapse rates. So typically when we think of dry adiabatic lapse rates near the surface, we're thinking summertime environments, thunderstorms, or really dry days like fire weather days. But we can actually get really narrow or shallow swaths or shallow layers of near dry adiabatic lapse rates near the ground. Now, why is this important? If you have near dry adiabatic lapse rates, it's really easy to mix parcels from the mid levels, like say where our maximum cold air advection is. It's really easy to mix those parcels down to the surface, and they manifest as wind gusts. And so imagine that if our level of max cold air advection is right here, you can infer that our strongest winds are at this level too. And so these strongest winds are going to be able to mix down to the surface and give you wind gusts of 40, 50, 60 miles per hour. The more prolific blizzards that we see, you're having frequent gusts of 40 plus miles per hour, 50s. I mean, they can easily go 60, 70 miles per hour. In fact, the worst blizzards typically see wind gusts of 60 to 70 miles per hour, which just exacerbates all the damage because you're blowing down power lines, you're blowing down trees. And so on top of all the snow, you've got stuff coming down, the infrastructure crumbling. That's what really gets people into a lot of trouble because that's how it knocks out the power. So this is something that we tend to look for in our really good blizzard scenarios. Here's an example from this. So watch the temperature profile. This is from Bismarck, North Dakota, and it's going to reset right there. And watch how quickly the temperatures fall off. And we have a maximum of cold air advection. It's just above the surface. But notice we have right where the cursor is, we actually have a shallow layer of near dry adiabatic lapse rates. And it's kind of moving past, so I apologize, but the winds at that level get to be about 40 to 50 knots in that little layer. And so you're able to mix down 40 to 50 knot winds to the surface really easily. And so this is the kind of profile that we're looking for in the forecast soundings. If we start to see this and it's like, we might have some problems because we might be mixing down really strong winds. Let that loop through again. All right. So here is just an example of all these different components. So earlier just a few slides ago, you saw the picture of the guy standing next to the power line. That's actually from this blizzard. This was March 2nd of 1966, easily one of the worst blizzards on record for the Dakotas. Well, no one that I worked with, was working during that blizzard, but it's just universally known. It's kind of akin to like the more tornadoes here. Just everyone knows it. It's in the folklore of the Dakotas. Just how bad this thing was. I think like thousands of livestock died. There were several deaths. It was just really intense. But let's break this down. So first we have our strong synoptic low. Unfortunately, I don't have the upper air data from this, but you can kind of infer by the strength of the low that there has to be something really strong aloft coming in. So we have our area of moderate to heavy snowfall. I forget how much snow fell, but it was, well above a foot across a pretty big area, but you can see it highlighted in the gray here. But again, it's where we would expect it, to the north and west of the surface low track. But also notice that we have a high pressure right here, and this is supporting really strong winds. So the winds through here are, that's 20 knots, 20 knots, 25, 30, 25, 30, 35 down here. So at this point, when the analysis was made, our strongest winds were actually down here in South Dakota. But this pressure gradient moved through North Dakota as well. So it's just a little bit later, but this is how we got our sustained winds of 35 miles per hour or greater. Oh yeah, so that's the general breakdown of it. And here's a more recent example looking at the whole picture overall. So we'll just go through this really quick. So one, strong synoptic low. Okay, here's our upper level trough with our jet streak. There's our region of strong to moderate heavy snow across the Dakotas. All right, so we got 2 of the 3. There's our strong pressure gradient. So our surface high is starting to build across northern Montana, southern Canada, and notice the pressure gradient across North Dakota. Those are sustained winds, 30 to 35 knots. So, okay, cool, we've got that. And then our cold air advection near the ground. So this is at 850 millibars. Notice that we have our maximum of cold air advection going right through the Dakotas as well. And again, this is a little bit later. It went through North Dakota earlier, and this was the result when that happened. So notice that, we did have some swaths of heavier snow, but down here, so New Rockford, Cooperstown, Valley City, only 3 to 4 inches. By North Dakota standards, that's pretty typical. But it was because of those pressure gradient winds that, man, this one packed a punch. And so these are some of the, images that were coming out. So we were sitting at the FO at the time, seeing these images, and we're thinking like, okay, yeah, this is a legitimate blizzard. So side rant. This is my personal rant. If you get me up here, I'm going to go on a rant at least once per talk. So a couple of years ago when I was working in North Dakota, there was a big snowstorm on the East Coast, and it was good snowfall. But there was one broadcast meteorologist that tweeted out a picture of like, oh, zero visibility on the interstate, whiteout conditions. Oh my gosh. And so I look at the picture and you could see like several hundred, yards down the road. I'm like, that's not whiteout conditions. You are misleading people. This is whiteout conditions. These cars are about as far apart as I am to Andrew Lyons right now. So like, that's the distance that these images are taken at. And past that, you can't see. If anyone's been in those conditions, it's scary. It is the scariest driving I've ever done. I've only done it twice, and I don't want to do it again. So that's my soapbox rant. This is whiteout conditions. Yeah. All right, so ground blizzard. So this is going to be really similar to our typical blizzard with one caveat. So here on the left are our typical blizzard ingredients that we just looked at. But we're going to take out the region of moderate to heavy snow and replace it with a pre-existing snowpack. All right, so let's look through an example of this. So we have our strong synoptic low. So right here, our low is over Lake Superior, just off the arrowhead of Minnesota, northeast Minnesota. Notice that this is 925 temperature. So we have really strong cold air advection coming through. There was just a cold front that just came through this region. Winds at 925 or 40 knots, up to 45 knots along the Minnesota, North Dakota border. So yeah, pretty strong synoptic low. Here was the pre-existing snowpack from previous days. So this was the snowfall from about 2 days prior. And generally speaking, this is a rule of thumb. You'll want to see at least 2 inches of snow on the ground before the winds start to pick up. And again, this is one of the caveats of winter weather forecasting. That snowpack has to be in the right conditions. So let's say your snow fell on a Wednesday, and on Thursday, temperatures got above freezing. What you're going to do is create a crust over that snowpack. And then let's say on Friday, it dropped below freezing again. By Friday, that snowpack has crusted over, and you could like drop a ball on it and it'll just stop on the surface. You could have like 35, 40 mile per hour winds. That snow is not going to go anywhere because of that crust. And so whenever I say you need 2 inches or more of loose snow on the ground, it has to be uncrusted. And again, this goes back to what kind of snow plates do you have? Do you have plates or columns or dendrites? It gets really complicated really fast. And you can break the crust if your winds are strong enough, but it's really tough to know when that's going to happen. It's a challenge. It's really tough, but it's a lot of fun too. So strong pressure gradient, this was at the surface about the same time. Again, this is the really typical setup. We have our surface high building across northern Montana, surface low somewhere in the upper Mississippi Valley into the Great Lakes. And then our cold air advection, this is cold air or temperature change at the surface over the past 3 hours. So you can see that's minus 12 Celsius at the surface over 3 hours. So that's pretty good cold air advection. And so, yeah, this was a really good ground blizzard case. And this is what it looks like on the ground. So if you're sitting on the ground in a ground blizzard, you might be able to look up and see blue skies overhead. It's really cool. But at the surface, if you're looking out ahead of you, it's just white. And so this is an example from this event where that's maybe a few hundred yards visibility, pretty reduced. This is that same storm with people stranded. And you can see, so here's some headlights from the other side of the interstate. But man, it's tough. It's tough driving conditions. And the best part about North Dakota and the Red River Valley of the North is that we have an interstate that runs right along where the winds are typically the strongest. So if we get a good ground blizzard, it'll shut down the interstate for at least a day. Oh, and here's the other cool thing. We can actually see ground blizzards from satellite. So this is the day snow fog RGB from GOES 16. Over here are some mid-level clouds, but notice these streamers coming out of Canada right through here. So these are actually plumes of blowing snow, and you can track them on satellite really easily, especially during the daytime. It's really, really cool. And so this has actually allowed us in recent years to pinpoint exactly where we need to put the blizzard warnings. So we can say this county should be, this county shouldn't be, because we can see it on radar or our satellite. And so if you're in one of these snow swaths right here, or streamers, again, this is what it looks like. It's not very deep, maybe only a few hundred, meters. And above that, it's clear, but if you're in it, it's pretty tough going. One thing to keep in mind is that this is that same loop on satellite. Notice that there's no streamers across northern Minnesota. That's because there's a lot of forest across northern Minnesota. So if you have really heavy forested areas or urban areas, that can actually, cause surface friction, blocks the wind. You don't get the blowing snow, and so you won't actually get blizzard conditions, despite any snowpack or how strong the winds are. So that's kind of a little caveat to keep in mind, is that if you have a lot of trees, it can kind of reduce your potential for blizzards. Quick recap, again, for a typical blizzard, we look for similar synoptic regime as heavy snow, but we're really looking for those strong pressure gradient winds. Look for that surface high building to the north of the low, and then see if it's going to last for 3 hours or more. For the ground blizzard, same deal, except we don't need falling snow. Instead, we're going to be looking for dry, cold frontal passages with really strong cold air advection and really strong gradient winds. Again, look for that building surface high to the north of the low, and see if it's going to last for 3 hours or more. If it is, got a ground blizzard. And just one last thought, just to show that all this stuff is really nuanced and it's really tough. This is an MCD that I wrote for blizzard conditions last month. In fact, 1 month ago today. And I want to focus on the last sentence there that I highlighted in yellow. I say, based on recent high-res guidance, portions of central and eastern Iowa may see wind gusts of 50 to 55 miles per hour over a 4 to 10 inch deep snowpack. All right, that seems like a slam dunk. I thought this was a slam dunk, resulting in a corridor of fairly intense blizzard conditions with near zero visibility is possible. Like that's for me, that's pretty strong wording. I don't typically say that, but I felt really good about this one. And what happened? So this line right here represents when I wrote the MCD. This is the visibility. The visibility actually improved after I wrote it. I was so frustrated by this. And actually, the thing is, like, notice that the wind speeds actually increased. So we were getting gusts. We didn't really get the gusts. I think that's kind of the key is we didn't get the gusts that I was anticipating. I haven't gone back to look at why I was wrong on the wind forecast, but I was obviously wrong on the wind forecast. And as a result, I really didn't get the visibility reductions that I expected. So yeah, it's tough. It's not always super clear cut, but you know, it's you learn as you go and do the best you can. So, and I believe we went just at an hour, so I think we're going to take a break before switching over to precip type and snow squalls. Does anyone have any questions on this? Yeah, has anyone been in a proper blizzard? Yeah, nice. How many enjoyed it? Okay, yeah, sweet, awesome, yeah.
So I was supposed to take my SAT, I grew up in the DC Metro, I took my SAT down in January 2016 blizzard.
Ah, okay, yeah.
Yeah, and we got about 2 feet of snow and we're out to school for 10 days.
10 days?
10 days.
That's awesome. So Robbie, is a quick break good to you, or?
5 minutes.
Yeah, 5-minute break, if that works. Meet back about 6:10.
All right, gang, I think we've got enough time. Mostly everybody back. I think got everybody back. So, hi, I'm the other Andrew, if you haven't met me, Andrew Lyons. So I'm also a mesoscale assistant fire weather forecaster at SPC. I'm also the winter weather focal point. So, winter weather is kind of some stuff that I do on the side away from our regular forecasting duties. Ironically enough, I absolutely hate winter weather. But I grew up in Ohio, so enough lake effect snow for a lifetime and all that. And I moved down to Oklahoma, thought I'd never have to like see snow ever again. And the first year I was here was 2021, and we got those back-to-back snowstorms. So that was wonderful. And I'm being sarcastic when I say that. So no, winter weather is actually really interesting, and we live in a really cool place because the default precip type here for winter weather is sleet. I say that only half jokingly. It is so hard to get snow here. And Andrew just spent the whole topic prior talking about heavy snow. But mixed phase precip here is super common. You guys went through the ice storm a couple weeks ago already. That and sleet. In 2014, when I was in school here, we had a sleet storm where it sleeted for like 2 days straight, and it was just sleet. It was thunder sleet, and then it was regular sleet, and then it was heavy sleet again, and then freezing rain, and then thunderstorms with sleet. So it was just sleet. So we'll talk a little bit about why that is and some interesting things. But if you've never experienced a sleet storm, also do not recommend, but you will if you're here long enough. So we'll talk a bit about ice and then snow squalls, which are kind of a new thing in the weather world. And this graphic background, this is not laziness. This was a style choice because ice is white. So we'll go with that. Anyway, we'll start kind of talking a little bit about the winter weather program at SPC. So like Andrew mentioned, heavy snow is one of our main MCD types. We actually write the most MCDs on heavy snow and blizzards, but we also do things for freezing rain, mixed precipitation types, and snow squalls as of 2021. And here's just an example of a mess, again, over Ohio. So what are we expecting? But there's heavy snow, there's mixed phase, there's freezing rain. It's all in one. Rarely do we get MCDs that are nice and pretty, but you can see all the different precip types there. So you may not know this, but all of the winter weather MCDs at SPC are rate-based. So we don't do anything with accumulations. Like if the Weather Service office here says, 4 to 6 inches of snow, they get to actually explicitly mention accumulations and all that. All of our stuff is rate-based. So for heavy snow, it's greater than 1 inch per hour below 7,000 feet, 6,000 feet, 4,000 feet. I'm the focal point. I should probably know that. Below a certain elevation, it's a 1 inch per hour rate. And then above a certain elevation, it's greater than 2 inches per hour. For freezing rain, it's greater than 0.02 inches per hour of freezing rain. And that also fits with the ice. So anyway, we aim for, lead times of a couple hours, and we usually run those MCDs a lot longer than the severe weather ones, typically 4 to 6 hours. And part of that's related to the type of forcing mechanisms that we just talked about. A lot of synoptic, but occasionally mesoscale details mixed in with them. Okay, so real quick, what is freezing precipitation? Well, at least in terms of the classic freezing rain, it's anything that falls as a liquid and then freezes on contact, through a super cold layer. There's also various definitions, ice storms or anything with greater than, a quarter inch of ice. But this kind of slide just kind of shows you, pretty much every winter storm has some sort of mixed phase precip. And when I say mixed phase, I mean frozen and liquid existing in the same area at the same time. So you get a lot of variation with these storms. And they look really cool. So this is a picture of a tree from, I've completely forgotten which ice storm that was, because there's so many here. I think it's like 2009 or 2010, but that is actually somewhere in Norman there. So it looked like it occurred pretty early in the year because there's still leaves on the trees, but you can see all that water has fallen down as rain, frozen on contact on those tree branches, weighed it down, snapped the poor tree, and you're left with an ice storm. So just some other ideas too, that when we're forecasting, winter weather and mixed precip, we're using a lot of observed and model soundings, probably even more than we are for severe, because we'll go through some examples, but those soundings are critical for determining precipitation type. That's probably the most useful tool you can ever use, is use those observed soundings and then taking those characteristics from the observed soundings and comparing them to the model soundings too. Every year, we also get a bunch of training on the precipitation types. If you guys know an ex-SPC forecaster named Joey Pica, he's really good on Twitter about showing different radar precipitation types using dual pole and also using sounding. So we talk to him every winter for our training too, just as a refresher. We get a bunch of training on trying to figure out those different precipitation types. And some mesoscale tools that we use, HREF, so the high resolution ensemble forecast. That's an ensemble of all the convection allowing models. So the HER, the NAM, the ARW, the NISSL-WRF, and the FP3. And also in there, we have QPF, so qualitative precipitation forecasts, and FRAM, which is the freezing rain accumulation model. So someone has developed a model that can guesstimate essentially how much ice you're going to develop or accrete on a surface based on the temperatures and the precipitation rates and all that. Okay, so this is just, again, a little bit of criteria, and here's an example of an impactful freezing rain MCD. I think this is from Central Texas, 2022-ish, but they had a freezing rain event, and it pretty much shut down San Antonio to Austin, kind of along that corridor. But those are some of the criteria that we use. So that's the 0.02 per hour or 0.06 greater than 3 hours. Okay. So we kind of already have talked about this a little bit, but just as a quick recap, just in the same way that you would have ingredients for severe storms, you need ingredients for winter storms. And for that, you need lift. So you need your synoptic ascent, your mesoscale ascent, you need moisture. It doesn't have to be a ton, but you need some amount of moisture that you are able to condense or precipitate out. And then you also need cold air. So that's the main thing. Those are the three typical drivers. And then this should look familiar. You've got your low pressure system, you have your fronts. This is an occluded cyclone, but you've got your warm conveyor. You have another conveyor back there, and this shows the cold conveyor wrapping around on the backside too. Okay, so again, we'll go over this pretty quickly, but sources of synoptic lift for winter weather, defluence and divergence, deformation. Andrew showed some great examples of that. Positive vorticity advection, so that's the QG theory arguments that we had kind of talked about. We kind of went over that quickly, but think jet streaks and troughs. Isentropic ascent, so this is the warm advection, or upglide or overrunning, if you may have heard that term. Orographic lift, so we kind of glossed over this one, but this is terrain. So air typically doesn't move through mountains. If it can, then you've probably got bigger problems. But again, that's that upslope component. Your terrain can also produce a lot of synoptic and mesoscale ascent. And then fronts, which we have talked about. And then It's a nice example of a strong cyclone. You can see a lot of that going on here. So you've got mid-level warm advection right here, got mid-level cold advection, probably have a lot of ascent going on in that eastern quadrant, probably a lot of precip that's developed on the north side of that. You see the RH values or the saturation values are pretty high right there in Canada. So that's probably indicating some snow or precip right there. Okay. So now switching gears kind of just towards ice. Have you guys ever seen a graphic like this? Yeah. This is a really good illustration, and I love putting this in here because this kind of does all the work. Really, the key driver with ice and mixed phase precip are a warm nose, so essentially a layer of warm air aloft, and the depth of the layer of cold air at the surface. So you can see when the whole column is cold or below freezing, you get snow as your precipitation type, right? There's no melting, there's no other factors that can influence your precip as it falls down. Now, let's say you've got snow aloft where it's nice and cold, but you've got a pretty deep warm layer. Well, it takes a pretty long time for snowflakes to fall, even just a couple hundred feet, a couple hundred kilometers, a couple hundred miles, oh man, I did it again, a couple hundred meters through that because they're light, they're fluffy, their terminal velocity is low. So it takes a long time for that snow to fall. So even, you know, your warm layers that aren't super thick, but relatively warm, they can melt all of that snow into liquid water. But if you've got a cold enough and deep enough air mass below that, you can actually refreeze those and pretty quickly, and that turns into ice pellets. So that's your sleet. And again, you can have infinitely many variations of this at the same time. But these are the kind of the main ones. And so thinking back again towards that deeper warm layer, again, you melt all that precip on the way down, but this time your air mass isn't quite as deep or isn't quite as cold. You can actually supercool that water really quickly as it's falling towards the ground. And it still stays liquid because it doesn't have enough time to spontaneously freeze, or there's not enough condensation or ice nuclei in there. And you just don't give it enough time to freeze, but it gets cold enough to where if it lands on a surface, because it's below freezing, that water won't spontaneously freeze. And that's how you get your freezing rain. And then this is the boring one, that's just rain. Nobody cares. But really, the main driver for precipitation types are, and neglecting all the microphysics, because I'm not going to touch that with a 10-foot pole. That is way outside of my wheelhouse. The main driver for precipitation types are the depth and the strength of the warm nose and the depth and the strength of the surface cold air layer, okay? So if you guys take away one thing, that's what I want you to take away. Oh, and then real quick, deeper and stronger for the warm layer, where we go. Deeper and stronger warm layers support faster and more melting. Surface freezing layers, the depth and intensity works in the opposite way. So deeper and stronger surface cold layers, more and faster freezing. So think about that. And you can also get some melting processes. So you could actually do a couple of different things to produce freezing rain. You can have it just be rain the entire time, or you can have it melt from that snow phase. I'm just going to skip through this a little quickly. Okay, so this is just kind of a climatology showing where on average you get the most freezing rain, or hours of freezing rain per year, or days of freezing rain per year. Look at that bullseye right over us, right in the southern plains. Anyone have any guesses why that is? Real quick. Where do we typically see cyclogenesis in the US? Just east of the Rockies, yeah. This is a preferred corridor for Lee low development and Lee cyclogenesis because our jet stream goes from west to east. So typically we're seeing lows generate in this area. What else do you need for low development? You need baroclinicity. You need a clash of air masses. I hate that phrase. I don't know why I said that, but you need a difference in air mass. So typically you have warmer air down here and it's relatively close to the Gulf of Mexico. So it's usually a little bit warmer, a little bit moister. And then you've got the plains, which you can easily advect cold air down the plains. And so you have that temperature difference right in that area. So a lot of times you're spinning up cyclones in East Texas, Southeast Colorado, Eastern New Mexico. Those storms will move east of us, produce precip, move off into parts of the Northeast and Eastern US. So yeah, we are actually a kind of a local maxima in freezing rain and mixed precipitation types across the plains. Absolutely.
So there's stuff across even Carolinas into the Northeast. Be really careful about what kinds of rain features are in those regions. And I'll just mention that topography is going to play a huge role sometimes in freezing rain events, especially along the East Coast and Northeast. That's a really big driver that we don't have to deal with it.
Yep. No topography. Woo. Okay. So real quick, I'm going to start with the graphic on the right. This just kind of shows you a cross section through a warm front, kind of that Norwegian cyclone model. And this should look really, really similar to that graphic that we showed earlier, showing the depth of the warm layer and all that. But you see all those different precipitation types and how you have ascent going up that isentropic surface. So the further you get away from your warm front into the deeper cold air, the more likely you are to have snow and frozen precipitation types. But as you get further closer to the low and the warm front, where you're still mixing a lot of that warm and cold air together, a lot of times you have that mixed phase or even all liquid. So, and here's just an example of the vertical profiles of each of those. You can kind of see the variation. So this is all snow, it's all below freezing with the dotted line. Ice pellets, there's quick melting, but there's also a deep cold layer. With freezing rain, it's a really strong warm layer, but really shallow cold layer. And then with all rain, basically the entire lower part of the profile is above freezing. So you're just melting the whole time. And then here is kind of where it's at relative to that cyclone model, you can see. So just another visualization. So this guy on the left here, this is from a paper that I have also forgotten the name of. I should have put the reference on there, so I apologize. But they did a climatology of freezing rain and snow and winter storms. And this is several of the most common patterns that they found for freezing rain in relation to surface fronts and lows and all that. So if you notice here, we've got a front, big cold front kind of stretching there with a big area of high pressure. Does that look familiar to anybody from the last couple of weeks? A couple of weeks ago, I got you guys off of school for a day. Yeah, that's a really common pattern here, where you get a really strong Arctic high that comes down. The air mass is usually pretty shallow, but you've got warm advection that rides up over it, produces rain that falls through and freezes. This is kind of the prototypical one where you've got the strong cyclone. You don't necessarily have to have a strong area of high pressure, but it helps because a lot of times that is the source for that cold air mass. And that's kind of a hybrid of both of them. I would say this one happens more frequently than either of the others. And you've also got some really interesting different variations in the surface pattern where you have local, impacts. But Andrew kind of pointed out a couple here. So notice those streaks across that area. What's in that area? Is there a mountain range over there? That's the Appalachian Mountains. How many of you have heard the term cold air damming? Yeah, okay, a couple people. So what happens if you're not from that part of the country or don't know, cold air masses like to get trapped up against those mountains on one side. And it's really easy to generate cyclones near and along that coastal area because you, again, have baroclinicity. You have strong jet streaks that are moving over that area. And anytime you have a cyclone and a trapped pocket of cold air right in there, and you precipitate over that, you can generate freezing rain. And so there's actually a lot of different setups that can produce cold air damming, snow, freezing rain, mixed precip types. So this is super common if you're from the Carolinas, even up into like Western Virginia, Eastern Tennessee. A lot of times they get ice, and you can actually see that on the climatology map too. So that's just some of the patterns that you can get. And there's a slide kind of talking about it. Again, you can get it several different ways, but typically you need some sort of cyclone. You need some sort of onshore flow because you've got a nice source of moisture out here over the Atlantic, and it's not that warm typically in the cold of winter, but you've also got a continental air mass to the north. And so you can actually trap that cold air right along the mountains and produce some pretty interesting freezing rain events. Okay, so real quick, Again, this is just another way to view some of the temperature profiles. I'm going to beat this into your heads about like what the profiles for each precipitation type look like, because that's going to be important for the forecasting challenge later. So again, here's rain. So we start off with snow, melts because we've got a really deep layer that's all the way above freezing right to the surface. There's no chance for that liquid to freeze back again. Sleet, again, it starts as snow. We melt through a fairly deep warm layer, but we've also got a pretty cold and deep cooled layer at the surface. And so it gives that time for it to freeze again right as it heads down to the surface. Here's snow. It's all below freezing. There's no chance for it to melt at all. And freezing rain, it starts as snow. It hits a warm layer. It's fairly deep, fairly strong. It melts all the way back into liquid, but we're really close to the surface. That cold layer, maybe only a couple 100 meters, maybe a kilometer, doesn't give it much time to freeze. So it's below freezing. When it lands, instantly freezes. Here's just another example. So this is from the December 20th, 2013 ice storm here in Oklahoma. Just a couple of things. So there's that shallow sublayer freezing. It's only about 1,500 feet. They are really, really small. So question, are numerical models really good at categorizing boundary layers and features that are not very deep? No. Do you see where I'm going with this? Precipitation type is really hard to forecast for, especially if you're just using models. So remember when I said observations and observed soundings are critical for precipitation type forecasting. Because knowing what those profiles look like is really key for determining your precip type. If you remember a couple of weeks ago, there was a lot of debate up until like right at the beginning of the event, whether or not we were going to be cold enough for that freezing rain event. You guys remember some of that? I don't know if everyone saw it, but internally at SPC too, we weren't sure because some of the models had it, some of the models didn't, and we weren't sure which one was correct. And then we looked at a sounding and we had that shallow cold layer and we were like, ah, crap, we're going to get a bunch of freezing rain. Sure enough, we did. So, and again, that other thing, the layer of warm air, that can also be tricky to forecast. So take care to check those observed soundings, compare them to the model soundings anytime you're forecasting for these different precip types, because little differences in those layers really are what determine what type of precipitation you get, what type of impacts you have, everything like that. All right, quiz time. Give it a second. What type of precip are we getting? What is that? Oh, C. Oh, okay. You're saying C, freezing rain. Okay, gotcha. Yeah. B, okay. Mixed ice and sleet. Okay. B, okay. B, all right. We're going mixed. Yeah. B, okay. All right. Oh, shoot. I don't actually have the answers on here. Well, you can tell I made these slides in a hurry. I'm pretty sure that's B. Yeah, on that one. So, whoops. So one of the key takeaways here, look at the depth of the freezing layer. It's fairly cold right at the surface, and that's relatively deep. That's over 100 millibars of cold air at the surface. That's probably enough time that you're freezing. So I'm also going to go B. All right, which one on this one? Everybody say C. All right, freezing rain. Yeah, you're right. Look at the cold layer. Oh my God, I keep doing that. It's not very deep, but it's relatively intense right at the surface. Like I can't quite read that, but you're almost, -6, -7 C. So that's pretty cold at the surface and it's pretty shallow. So, and look at the warm nose on that too. Ain't no snowflakes making it through that. They are melting all the way. So that is a freezing rain sounding. If I saw that again, I would be very sad. All right, easy peasy. Which one's this? Oh, got some disagreement? All right, everybody's kind of, yeah, it's snow. It's all below freezing. You're pretty close. This layer is kind of isothermal, but it's still below freezing. So you're right. It's snow. Okay. So we've kind of simplified it. You know, we've made it look relatively easy. Just a quick point that precipitation type is really tricky. But just some simple rules can improve your forecast greatly. So remember, check those observations, check the air masses upstream and downstream. A lot of our freezing rain or our winter weather events here have warm advection. Strong warm advection can really screw up your precipitation types if you are not accounting for the magnitude here. A la our just last snow event. We never really had the cold air. So one thing that you always want to make sure is that you've got your ingredients, and simple checks like that can be really useful for just simple forecasting for this frozen precip type. So anybody have any questions on ice, mixed phase, stuff like that? Yeah, oh, we've got one question too. So let's go ahead first. Yeah. Yes, it absolutely can. So all of the soundings that I have shown you have basically been near saturation. But if you have a layer of dry air near the surface and you are dropping precipitation through that, how do you think that could change that layer? Exactly. Yes. So saturation can be critical for that. If you're saturated right at 30 to or 35 degrees, you probably aren't going to cool it very much unless you've got a really cold layer of air above that you're able to mix down. So yes, saturation is really key for things like wet bulbing, evaporative cooling, and also whether or not your precipitation makes it to the ground. You can actually have cases where if you're just replacing that dry air with say a dry, cold source to the north, and you're not able to get enough moisture in, that can screw up a winter weather forecast too. Are you all familiar with the term, the dry slot? That likes to happen here a lot too, doesn't it? Yeah. Woodward, gets a nice snow, Enid, all that, and we get nada. Yeah. So saturation is critical. And I should have actually put that in there. So yeah, that's a great point. I had another comment too. Yeah.
Where the every 20 seconds.
Mm-hmm.
That has been great by comments, so thank you, Brad.
Yes.
So one thing that I've seen count many times, and this happens in this area too, is that if you have a layer of the atmosphere that's really close to freezing, like we do in this sounding, very small local changes in the profile can lead to mixed precipitation types and like rapid switches between the two. And it can happen over the course of like miles. And you can have I've seen cases where you have every single precip type in the same county, basically. And it's just because of small differences in the temperature profile over a geographic region. And so you might have snow in one place, rain in another, freezing rain somewhere else because of small variations. And again, you mentioned the models having trouble with that. The models really struggle with that kind of variation, like we did yesterday. And that's where observations, again, is so critical.
Yep. And we always say 32 degrees Fahrenheit, 0 C, that's, when ice forms or whatever, that's a rough rule. You can have snow with surface temperatures well above freezing. I've seen snow with surface temperatures near 40 degrees. So you can have things persist. You just get more likely to have freezing precipitation right at that 32, 33 degree. And then beyond that, that's much colder. But anytime you're within a couple degrees of freezing, you can have essentially any precipitation type. So, and it can persist, change back and forth really quickly due to local variations and all sorts of microphysics stuff. Yeah.
There's something interesting too, is a lot of times like some of the Wisconsin we get dry spots and it actually well freezing out the entire column, but you could actually get freezing drizzle when it was
Yes.
low freezing because you have not enough, too dry in your drizzle.
Yes, thank you very much, because that was my other point. You mentioned saturation. All of this, I've talked about top-down saturation. You can actually saturate from the bottom up. if you have a really narrow, thin layer of water, essentially liquid water vapor at the surface, you can actually generate freezing fog, freezing drizzle, but it's not heavy enough to produce ice crystals because you're not cold enough. So you're right within that freezing, supercooling range, but you're not producing enough ice crystals to produce snow or other precipitation types. Bottom-up saturation is really common in upslope regimes, and in places like the dry slot. So anytime that you have variations in that saturation or temperature profile, you can get different precipitation types. So thank you, Andrew. That was awesome. Yeah. Any other questions? Any comments? No? Okay. All right. So we'll kind of move on to snow squalls. How many people have heard of the term snow squall? Okay. So it's kind of new. They were kind of first discovered in the northeastern US about 20 or so years ago. The terminology has been kind of evolving with that. So what I'm going to present, there's a big disclaimer. A lot of this is kind of new research and new ideas that are not necessarily well established in the literature, but it's getting there. And I've got some research on that I'll try and show you guys too. But it's kind of a mishmash. So snow, that should be obvious. That's the precipitation type. But a squall in nautical terminology is a sudden change in wind or precipitation. So squall line, that sort of thing. But this is actually just a really short-lived, intense burst of moderate snow and strong winds. Occasionally there's a flash freeze, so you'll actually drop below freezing really quickly with these types of systems. But they can be super impactful because, like Andrew mentioned, if you've got that blowing and heavy snow, you've got a blizzard. So these are almost like little short-term blizzards that can produce really intense bursts of snow, low visibility, strong winds. They suck to drive through, let me tell you. And they can often be fatal. So a lot of times you'll see like pileups in the northeastern US or even in the central plains and all that. Sometimes these are caused by snow squalls. So they're really impactful. So just a little bit more background on these. They're essentially, convection. So they have a lot of the similar properties of thunderstorms, but they're not producing thunder or lightning most of the time because they're shallow. That they've got things like pressure, rise and fall couplets. So they're moving air and processing the air like thunderstorms, even though they don't always have lightning. And a lot of times they've got those outflow winds, and then occasionally they will have lightning. Real quick, does anyone know why it's hard to generate lightning when you only have snow as a precipitation type? Yeah. Yeah. Mixed phase precip is the main driver because you're able to transfer that charge more effectively. Anytime that you have lightning with purely snow, you should check and see what man-made structures are there. Some research has come out of SPC and some other places, but upwards of 90% of all thunder snow cases are actually static electricity induced by buildings. And lightning or towers, wind turbines are a favorite because you're hitting a lot of stuff off of the wind turbines and they're made out of mostly plastic and carbon fiber. Anyway, that's an interesting aside and we'll get into some of that, but sorry, Jim Cantori, most thunder snow is not actually real in the sense of that. Oh man, I'm doing it again. Real quick, there's also some emerging research that snow squalls can take different convective modes. So think like how we have different types of thunderstorms, single cell, multi-cell, supercell, squall line. There's some research that's emerging that snow squalls can also behave differently based on other environmental parameters like vertical wind shear. So I like to joke, this is a climatology-ish of snow squalls because no true climatology actually exists. It's a bit melodramatic, but we have no idea where these occur, when and why and how, because it's so new. There have been some attempts. So this is a local climatology from Burlington, Vermont. We'll get into more why they know that in a little bit. Showing just a couple of months or counts of snow squalls over a couple of years, and you can see they're most common in winter, kind of towards the end, February, March. And then this is a plot of something called the snow squall parameter. So this is a composite parameter like STP, but it's designed to detect snow squalls. And this is for parts of Wyoming, Colorado, Utah. You can see this is the relative frequency, or essentially the percentage of hours that have a snow squall parameter greater than 0.06 or 0.6. And so you can kind of see which areas line up. No surprise, it's often found in the mountains where it snows a lot. And we'll talk a little bit about that, why that is, because of the ingredients that go into that parameter. But just some quick overview points. They pretty much occur anywhere throughout the US in the cold season, increasing in the fall, kind of continuous through winter, and then kind of slowly tapering off in the spring. We don't actually know where or how often these occur in other places, or how often the conditions that support these occur. We'll get into some more of that, but they're mostly tied to the diurnal cycle. So just like thunderstorms, how thunderstorms are more common in the afternoon through evening, we're finding that these are also more common in that time frame, which tells us that they're tied to diurnal instability, which makes sense. They're convective features. Okay. So one thing that I'm working on at SPC is actually a climatology of the snow squall parameter. So we're trying to calculate the snow squall parameter on ERA 5 and all these other reanalyses and go back several decades and trying to find when and where these occur. This is a synthetic climatology because we're using a proxy. It's actually really hard to find these things in the wild when you're just looking at radar data because they're so short. You know, you're talking about capes that like are maybe 100 joules per kilogram if you're lucky. You know, compare that to supercells and tornadoes out here that 2,000-3,000 joules per kilogram a cape. It's minuscule. And these can often only be, 2 to 3 kilometers tall, but they're convective features. So it's hard to see these things on radar. It's hard to find them on satellite. And I really don't want to go through thousands of hours of METAR data to find when these things are happening. So I said, let's try and use the snow squall parameter to find these environments, and then we can narrow it down from there. So we're working with a couple people. This is Weather Forecast Office, State College, Pennsylvania, Burlington, Vermont, and then the Weather Prediction Center too. And then this is just some background. So Victor Gensini and Harold Brooks, who works here, did the same thing to investigate tornado environments from a long time ago using reanalysis. And so you can see there's kind of a correlation between their composite parameter and tornado reports. That's kind of what we're using to justify ours. And we're going to check out ERA 5, which is the EC-MWF reanalysis, and the RAP mesoanalysis here at SPC. And then we also looked at NAR too, but NAR is bad. So I'm going to have to check something else out. And then this is just what some of the initial stuff looks like. So this is the hours of accumulated snow squall parameter from January, February, and March of 2003. And you can see there's a bunch of stuff up in the Northern Rockies where it's cold. You've got moisture and it's windy. So that kind of highlights that well. And you see the parameter also highlights the area it was designed for. So parts of New England, parts of the Eastern Great Lakes, that sort of thing, all the way down parts of the Appalachian chains. But what we're also finding is that occasionally these environments happen here. We're in that lower hours range, so it's not super frequent. But then if you notice across the Northern Plains, the Red River Valley, Eastern North Dakota, parts of Northern Iowa, Southern Minnesota, there's a nice little corridor of higher, hours of accumulation there. And that's typically where we see those blizzard conditions and all that stuff that Andrew just talked about. So there's kind of an overlap between these ideas, and it's really because they're winter storms. And so we're learning more and more about these, and you're kind of seeing some of the features in there. Now, this is just another way to look at it. This is just relative frequency. So this just shows up a little bit better, and you can see higher relative frequencies in those areas that we talked about. Okay. So, oh man, I'm going to move this window around a little bit. So we talked about, snow squalls, kind of what they are. Let's kind of talk about how they occur now. So going back to that idea of them being like thunderstorms, you know, they are convective updrafts. And anytime that you have a convective updraft, you have to have a convective downdraft too. So you may have seen a similar plot like this showing cross sections through a squall line. Well, this is just a cross section through a snow band that behaves like a squall line. And this is really what a snow squall is. So you've got an updraft, you're producing precipitation. You usually have strong pressure perturbations down at the surface and in the updraft. And that's how you get really strong winds. And you also get really heavy snow in that really narrow band. They are low-topped quasi-linear convective systems. That's all they are. They often have low CAPE. Sometimes it'll display as 0 on model guidance. Again, models are really bad at small changes in surface temperature and surface moisture. And these environments are really, really hard to detect. They can also be related to lake effect bands. So again, thinking about our cold environments or our cold season ingredients, moisture, a source of lift, and cold air, Great Lakes have all of those. And so you can actually generate winter storm environments on a mesoscale basis off the Great Lakes. And occasionally you'll see snow squalls come off the lakes like that. They'll start as mesoscale bands on the lake as lake effect. They'll break up into individual segments and they'll continue on producing snow squall conditions downstream. Okay, so here's kind of a snow squall proximity sounding, kind of what they look like. So you can see they're mostly saturated in that lowest couple kilometers. Again, that's saturated enough with respect to ice to produce snow. But you notice that boundary layer, it's pretty steep lapse rates in the lowest level. There's a little bit of an inversion here, but even through that layer, those lapse rates are fairly steep. So you're able to generate convection in that layer. And you can kind of see it. This is a little bit better. This is the HRRR model sounding. You've actually got positive buoyancy. It's not a ton. And then you also have strong winds right in that layer too. So these are essentially thunder snowstorms that don't have lightning, but can produce a lot of impactful weather at short terms. So just really quick, oops, sorry. Go away. All right, whatever. I can't read that first one, but it's fine. You know, there's usually these small unstable layers with lapse rates, you know, greater than 5 C per kilometer throughout that lowest couple hundred meters. And that's what's driving these convective processes. You're also getting strong winds throughout the column. So remember, we talked about some of the wind potential with these. They're blowing snow. That's what causes part of the visibility restriction. You actually have strong winds within a convective boundary layer. And so you're mixing a lot of that snow and blowing snow together with that buoyancy. And in this case, you don't have quite as much saturation at the surface. So if you do produce precipitation above this, you can wet bulb down really quickly. And you can actually go from above freezing surface temperatures to below freezing surface temperatures really quickly too. So that's a flash freeze component of that. Okay. So this is the actual snow squall parameter. And this looks really complicated, but it's really not. This was developed by the Science and Operations Officer at the Burlington, Vermont office. His name's Peter Bonakos. He actually used to work here at SPC. He was a meso-A for many years. And he took that interest in convection and also interest in winter weather because he was from New England. And he said, well, I'm going to use what I've learned there to help forecast these snow squall events. And so that's what he did. So the snow squall parameter is really just 3 terms. It's a moisture term, it's a low-level instability or buoyancy term, and it's a wind term. You multiply those all together, and that gives you a value. Anything greater than 1 shows conditions that are usually favorable for snow squalls. And you can see you just need enough saturation, so 60% relative humidity in the lowest levels. And this term looks really confusing, but all this is a theta E lapse rate. So think about lapse rates. That's just a change in temperature with height. All this is a change in equivalent potential temperature with height. So we talked about how these CAPE environments are not very strong, right? That they're usually pretty weak. So this is just a way to try and diagnose instability with those weak environments. Because CAPE doesn't always show it super well, they found that this parameter was the best thing that they could substitute in to show that buoyancy. Because basically anytime you were generating positive CAPE, you had a positive theta E lapse rate. And they're usually pretty small changes, but this is how they derive their buoyancy. And then you also have a wind term, so 9 meters per second. I think it's pretty darn close to like 28 to 29 miles per hour. So you basically just need strong winds in that lowest 2 kilometer layer. That's your blowing snow and strong wind component. So that's all of these contribute to low visibility, heavy snow in brief bands, and flash freeze potential. So they typically range from like 1 to 5. It was developed based on the NAR data. But in that 2 to 3 plus range, that's when you get really significant snow squalls. So I think I showed you, yeah, this example. So the scaling is not quite correct, but you can see values of like 15 to 20 up in there. So it's non-dimensional and it does go as high as you want. So you can really see how they're located along that cold front, strong forcing right off the Great Lakes. Okay. Again, this is just a way to show the sensitivity. So the most sensitive part of the parameter is the buoyancy or the instability term. So you see it has the steepest slope when you change it. So again, that just shows you how sensitive these environments are to small changes in buoyancy, which is why they're so hard to forecast for. Because again, models are not super great at that. Local changes can really influence that. Just some other research is finding that this may not work in other parts of the country or may not work in all scenarios where you're producing snow squall-like conditions. So it's something to keep in mind when using this parameter, but it's extremely sensitive to small changes in buoyancy. Okay. So we've talked about kind of what they are, how they form. This is what they look like. So, which looks like not a whole lot, but you've actually got a lower cloud base. It kind of looks like a shelf cloud. You know, if you had a line of thunderstorms coming across, this is kind of that lower shelf cloud where you're producing that slab lifting, you're producing your heavy snow, you see the low visibility underneath there, but they're just like little squall lines. Here's kind of a classic case. There's typically a strong mid-level synoptic system. So think about the synoptic systems that Andrew was talking about, a big deep trough, a strong low with a big cold front trailing off of it. That's the prototypical snow squall scenario in the northeastern US. Yep, you got a strong front, low-level frontogenesis. So that ageostrophic, that frontogenical circulation, a lot of times that's helping to drive snow squalls right along the front. But there are usually these strong bands. The lakes can also influence them by providing extra moisture, extra buoyancy. But that's the most common type is these squall lines. You can get cellular cases, but it's not a lot of research on that right now. So here's another example from January of 2013. So this is the snow squall parameter up here in Canada. And then you also have lines of surface pressure and winds. And you see right on the wind shift of a strong cold front up there, you've got really strong values of snow squall parameter. And then the Canadian radars are showing that band of heavy snow. It's not perfect. It's probably in its initial stages of forming, but it's showing up right where you've got those higher values. And here's just another example from that day showing the strong upper level trough. So you've got strong ascent on the jet streak there, just the north. You've got a strong upper level low, and there's a lot of baroclinicity even at 500 millibars. So that tells you how strong that front is, and you have a really strong frontal circulation that's helping to produce those snow squalls. Just looking a little lower, so here's the saturation, the 925. And again, you see this is the buoyancy term. So it's showing that change in theta E with height, where you're able to generate positive buoyancy or convection, even when CAPE doesn't show up very well. I should also add, real quick, does CAPE take into account the effect of ice? I'm seeing a lot of head shaking no. And I know some people in here have worked on things like that recently. Yes, so most CAPE, the way it's calculated, does not take into account the effect of latent heat release from ice. So just like how relative humidity with respect to ice is different, latent heat release with respect to ice is different too. And if you're not calculating that, that can drastically alter your CAPE calculations. So that's part of the reason why they also don't use CAPE in the snow squall parameter, is because it doesn't always account for the differences with ice. So that's also something to keep in mind. But you can see that buoyancy term, they're generating the positive buoyancy. You also have a lot of convergence and a lot of frontogenesis along that front. So all of those factors are there to produce precipitation on that. And then this is just another example. So you saw those two pictures earlier. This is what the snow squall parameter looks like right along that front. It's pretty narrow, but it's a strong band showing those enhanced values. And sure enough, on radar, you've got these little narrow squall line like bands that are producing heavy snow, strong winds, and low visibility right underneath them. So that's a classic case. I talked a little bit earlier about the differences. So there's some research from some people at South Dakota State, and I think she is now at Penn State doing her PhD, Leanna Bender. But she found that if you vary the amount of wind shear in the layer, and again, that's a small layer that these storms are active over, you can actually generate different types of convection. So the banded cases, a lot of times those were stronger, more coherent wind shear. Whereas if you don't have as strong a wind shear, you get these more cellular. Now it's debatable whether or not those are true snow squalls. You can make an argument that those are just snow showers, but they're operating on the same procedure, essentially the same process of strong convection generating heavy snow. So just wanted to show you an example of that you can get cellular or, more linear features based on your environment, like vertical wind shear. Yeah.
So kind of go off of that, theoretically,
Mm-hmm.
is it possible to get, you've probably seen where I'm going.
I think so.
Like snow supercells, right? Where you have strong, where the wind shear. I'm not going.
Yeah.
Snow native, right? But
That's a great movie idea, though. Yeah.
But is it theoretically possible? I feel like obviously that would be pretty hard to get.
Yeah.
Here's what your thoughts are.
I would say probably. We've seen mesocyclone-like features in lake effect snow bands. Anytime you have a convective updraft, you are theoretically able to stretch streamwise vorticity and generate things that appear supercellular. Andrew, I don't know if you have any thoughts on the idea too.
Yeah, it's actually, that's something this at work. So I think the biggest issue to run into is that as you get colder in your profile, you have less and less moisture, right? And kissing ratio is decreasing. And so you're just not gonna, your air is just too dry, you have much buoyancy. And so when you can get buoyancy, but like you said, the soundings like it's so minuscule that are you really gonna be able to generate enough earth velocity to do a whole lot with?
You're not gonna have hail and snow.
Probably not. Yeah. Yeah.
I don't know.
So the answer is maybe, I don't know. I would, yeah, do it. Yeah. Someone, whoever's researching that, do it. Yeah. There is a lot of potential. That is the difference. And vertical shear and distributions like that are going to be related to how your boundary layer is structured and things like that. So I would say yes. This is so new. There's not even really any published research on this type of thing. So if you're looking for a dissertation topic, it's an interesting one. But yeah, I'd say that probably the boundary layer is the most influential part of that. There are some recent cases that have popped up that these could actually be elevated above the surface too. But again, this is so new that nobody really knows yet. But it's an interesting idea, and I think you're probably barking up the right tree on that one. That these could be a bit more related to things like boundary layer turbulence and different types of convection in your boundary layer. So yeah, great question. Yep, and then this is just a little bit more. So this was some of the justification, like there was slightly stronger vertical shear for the banded cases versus the cellulars. I'm not going to go into all this again. This is just a quick research. So kind of along the same lines, we talked about how the snow squall parameter may not work super well in all parts of the country. There's kind of an emerging group. I did most of my time at Cheyenne and Grand Junction, Colorado in the Western US, and we found that the snow squall parameter didn't always work for events that we would consider snow squalls or snow squall-like. So you can get snow squall-like conditions with heavy snow showers that can occur in frontal and banded configurations, but sometimes they occurred in the absence of these fronts. So we're not 100% sure what is causing them, other than local buoyancy and things like that. But there's a pretty big gap in understanding right now about what's going on. So that's part of the reason that I wanted to do the snow squall parameter climatology, is actually look and see if these types of environments are different, or if they're not being captured, or what's the difference. But quickly see what one of these looks like. That is really loud, I'm sorry. But yeah, so anyone that wants to argue that that's not a snow squall, I'm happy to talk to you outside. Yeah, but those are, imagine trying to drive through that at night. Like, it's horrifying. Like what Andrew said with the ground blizzard stuff, it is terrifying. And we routinely had, pileups, 100, 200 cars on Interstate 80 in western or eastern Wyoming and western Nebraska. So it may not matter if these are, the exact same thing scientifically, they have true impacts. So that's just one example I wanted to show you. Sorry, that's going to be really loud. I think we're kind of moving into the next topic. So I'm actually going to end my stuff here. This is just a little case study. Anybody have any questions about snow squalls? Kind of some of that stuff? That's a lot of information, and that's just the tip of the iceberg. Yeah. Yes. Yeah, that's
All right, guys. So for the sake of time, we'll go ahead and get started with our forecasting activity. So is there anybody that, well, I'll put it this way. If anyone doesn't have a laptop, team up with someone that does have a laptop. So you might have to move around a little bit. All right, so if we've all got our teams, we've all got our laptops out, awesome. So let's get started. So congratulations, you've all been hired to the Norman WFO as forecasters. So it's your first day on the job, and we've got some winter weather potentially coming in. It's your job to help decide, do we need headlines? Do we need a blizzard warning, ice storm warning, winter storm warning, or just a winter weather advisory, or no headlines at all? That's your task. So what we're going to be doing is we're going to be iterating through some data. We're going to start at 48 hours prior to the start of our event, and then go 48 hours, 24 hours, 12 hours, and 6 hours. So you'll have 4 opportunities to look at the data and decide, do we need to issue headlines? So we have an online tool that we're going to be using to issue our headlines. So we have a URL up here, this thing right here, weatherwatcher.us/map/winter. So go to that URL and we'll quickly talk about the online tool we'll be using.
And Andrew coded that all, so thank him. He's got awesome tools that you guys can mess with all that stuff, so.
So is everyone on this page up here or something close to it? It might take a second to load, has to load the CWA boundaries. So this is the tool that we're going to be using. So I'll start off by pointing out up here, we have 4 different headlines that we can do. We can do winter weather advisory, winter storm warning, ice storm warning, or blizzard warning. So let's say, for example, we want the winter storm warning, and let's say we want Cleveland County to be in a winter storm warning. All we have to do is just click on the county and it turns it the right color. But let's say we want the whole state of Oklahoma to be in a warning. Let's go to this little marker thing right here. And we're just going to draw a polygon. And then close off our polygon, and all those counties are now in our warning. Also,
No school.
school's been canceled. If you, you'll see that if you click on and off counties, it toggles the county on or off. If you want to change a county's type, just switch hazards and click it, and it'll switch it. All right, so that's the tool we're going to be using. So as you go look at data, you'll make your decisions. Make your forecasts on here, and we'll talk through it and see who's forecasting what for where. Back to the PowerPoint. All right, I'm going to go to slideshow view now. So again, we are just WFO Norman forecasters. So we're only concerned about our CWA, which is highlighted here in black. So we don't really care about Tulsa. We don't really care about Dallas, but we do have a small sliver of Northwest Texas. So don't forget about them. Wichita Falls, they're people too. So they are Texans, but we won't hold that against them.
We love them.
Yeah. All right, so let's move on. So this is what the hazards will look like. I kind of demonstrated it. So we'll have red for blizzard, pink for winter storm warning, purple for ice storm, and blue for winter weather advisory. No color for nothing. And this is what criteria we're going to be going with. So again, here locally, this is actually the heavy snow criteria for winter storm warning is 4 inches or greater. So if we're expecting snowfall less than 4 inches, go winter weather advisory, or freezing rain less than 1/4 inch. Winter weather advisory. Snowfall amounts over 4 inches, winter storm warning. Ice storm warning is any freezing rain over 1/2 inch. And blizzard warning, 3-hour duration of heavy falling snow or blowing snow, reduced visibility, and winds above 35 miles per hour. All right, so, and we're going to come back to this, so you don't have to memorize it. We'll see this when it comes time to make our decisions. So, oh, and this is the last thing I'll do before I turn it over. So this is our pre-existing snowpack 48 hours prior to the event. So if there's snowfall at the 24-hour mark, be sure to take that into account if we're dealing with a blizzard. But this is what we're starting with, basically no snowpack over the entire state of Oklahoma. So hand it over.
Okay. So like Andrew said, congrats, you got hired. First day on the job, you're doing the forecast desk. So pull up the 300 millibar chart. Here's what you got currently. So any big features that you guys see that are kind of interest? Yeah. Yep. And I think you were pointing at it too. So yeah, big old trough on the West Coast. Otherwise, it's kind of zonal. Yeah.
See a small where that enhanced area of Omega is, or negative Omega, small work wave there.
Mm-hmm.
That could locally increase upward line.
Yeah. Yeah, there's a little bit of convergence. I'll tell you the main player is this guy out here. So remember, because we're 48 hours ahead of time. So so this will probably be more impactful for places downstream, but you're absolutely right. That is a little shortwave embedded in there. There's also maybe hints of a little shortwave kind of on the base of that trough back there. And it's mostly zonal, but it's pretty strong. So just thinking about our QG arguments, again, we went over QG in our other class today on this exact same example. So there's 2 factors that can support deepening of a trough. That's positive or differential positive vorticity advection, differential thermal advection and positive vorticity advection. So 300 millibars is a great place to look for one of those things, positive vorticity advection. And so anytime that you have a jet streak kind of on the backside of a trough here, which you've got 100, 110 knots on the backside of the trough here, you've got extra vorticity that's back here. So you're advecting some of that in there. You can actually deepen your trough when you see that type of configuration. So hint, hint, this trough might be deepening a little bit in the next couple hours.
Just for clarification, I apologize. My graduate student, I didn't realize it's plotting the AV sort of wind bars. So if you're looking at.
Oh, I
wind
didn't
bars,
either.
Hey, that's not 100 knots. That's because it's the AV stroke of wind. So that's the part of the wind that's not in balance with pressure gradient.
Yeah. So I was just the velocities here. That's just referencing the ISO lines there that fill. But those barbs, yeah, good call. I didn't even realize that either. That's the ageostrophic component. So thinking back to your jet streak model, you can actually see the ageostrophic components of the wind right there. So your stronger winds on your exit region of the jet. So we've solved it. It works. Wow, look at that. Anyway, just be thinking about this overall synoptic pattern and picture as we go through the next little bit of data. Okay, still 48 hours in advance. This is now 500 millibars. Again, you see the main strong jet streak on the left side there. It's a little bit further north, still displaced a little bit. Well, take a look at the temperature gradient. How strong? You think that's a strong temperature gradient or a weak temperature gradient? I already gave away the answer, sorry, but it's strong, yeah. So there's a lot of baroclinicity there. So hint, hint, that's another potential indicator that this system might be strengthening over the next couple of hours or next couple of days, because we've got that baroclinicity there. We've got that air mass difference. Areas of low pressure really like differences in air mass. Again, that's kind of the main feature. Everything else out here, it's mostly zonal. These do go on to produce winter weather and some precip further east. But our main guy, we're still kind of looking out there. Okay, down to 700 millibars. This color fill, this is relative humidity greater than 70%. So we're looking for things like saturation in this layer. And remember, we're forecasting for Oklahoma. Are we saturated currently? No, yeah, we're pretty low. There's not a whole lot of moisture with that right now. There is some upstream. But it's actually looking fairly dry. So that's something to keep in mind. Again, thinking about that saturation argument for precipitation type. What type of precip are we going to get? Okay, 850 millibars. Okay, what's the first thing you notice about 850 temperatures over Oklahoma? Very warm, pretty warm. Yep, we are 10 Celsius ish around Norman. Remember our cold or winter storm ingredients: lift, moisture, and cold air. Do we have a lot of cold air right now? No. What about further north? We've got some, we're down up to negative 10C in Minnesota. And we know that this trough out west is probably going to deepen a little bit. Maybe help bring some of that cold air down. But the first thing that I notice when I see this plot is that there is not a lot of cold air in the US at this time. So thinking about our ingredients, who knows, this could be a bust case. We could be really mean and give you a potential winter storm event that has no winter weather in it. So just be thinking about that. Looking a little further south, there is moisture, so that's the dew point. So we do have moisture, and we know we have synoptic lift, but we may be missing one of those ingredients. So think about that. Here is near surface temperature, or surface temperature, dew point, and mean sea level pressure. So with our trough out here, we really don't have a surface reflection of that yet. It's still farther west than the Rockies. We don't have a strong area of low pressure, but we do have a front. It's kind of lying over us. There's that moisture. So dew points in the 50s, 60s. The purple line is freezing. So again, all of our cold air right now is locked up in the northern US. So we're 48 hours ahead of when the event may occur. We may need some help getting that cold air down there. And then this is near surface wet bulb temperature. So Again, just showing our freezing line is a little bit further south with the wet bulbing. Oh, sorry, you got fired for having your phone on at work. I'm kidding. Okay, we're gonna go through some soundings real quick. So here's Norman. So 48 hours before, like we talked about, it's 64 degrees. It is a beautiful day in the Norman Hood, and it is dry. It is a 35-degree dew point, but look at that hydrolapse. Oops. We got some work to do, folks, if we're getting our winter weather going on that. Not a northerly wind barb in sight either. So right now we are continuing to warm advect. So we are trying to drag even more warm air into Norman at the same time. Okay, Amarillo. Also pretty warm, also pretty dry. That look like a particular surface feature to anybody? Anybody familiar with the Southern Plains? What tends to happen between here and Amarillo? It's an elevated mixed layer. Yeah. This is probably behind a weak dry line. So do you get a lot of snow behind dry lines? Yeah. So interesting. But it's, again, pretty dry, pretty warm. Something we're going to have to change if we're talking about snow. All right, Dodge City. All right, anything different? A little more moisture, a little saturated. What about those surface winds? Northerly, yeah. So we've gone up north. We're now north of the cold front, or a potential front up there. So we are cold advecting at the surface. So we are trying to drag some of that colder air down. It's still pretty warm. It's still pretty dry in the mid-levels.
Profile, shut it to the left on the diagram, did that potentially look like a snow squall?
What if this is a snow squall case? All right, North Platte, Nebraska. Again, we're a little further north. What do you notice about those winds in the lowest couple kilometers? Northerly, yep. A little bit stronger, yep. So, and it's a little cooler. So we are cold advecting slowly. Look at those lapse rates too, 8.5, that's pretty good. If you shift that profile to the right, are we talking about tornadic supercells in North Platte, Nebraska? Yeah, so it's a little bit better. We're slowly starting to moisten up the profile from the north. We're advecting some of that cold air down. Okay. You know, we tend to issue those winter weather highlights about 48 hours in advance. What are we doing? Yeah. Anything to add on this one? And obviously we're purposefully limiting your information so you guys don't know, and making it hard, but we want you to think about all the features that we've seen. So when if you do want to draw any areas, you can. If you don't want to draw any areas, you can also do that. But let's think about ingredients. So we've got a trough to the west. It's potentially amplifying over the next couple of days. Most of our cold air is locked pretty far north, but we do have a front, and we do have some cold advection dragging us down. And looking further south, we do have some moisture, but we're lacking some kind of overall convergence of those ingredients at this time. So just out of curiosity, is anybody drawing winter weather highlights? Yeah? That is the lowest that you can go. Yeah. Yes, you will. Yeah, you can. We'll do this every 12 to 18 hours. So you don't have to do it now if you don't want to. But just be thinking from a communications perspective, do people like to know information earlier? You know, so you kind of got to balance. The forecast may be uncertain, but do I need to tell people about potential weather impacts? So, yeah. Okay, so you're kind of worried about the upper level system, kind of how it's coming through. You think we're probably going to cool down, may get some precip type. Is anybody else drawing anything? I'm just curious. Yeah, just the Norman CWA. Yeah.
My biggest concern right now is depth of moisture.
Okay.
I was at the desk, I would have some model data to figure out.
Yes, you would.
So assuming we have enough moisture reduction, I would also, given that still, hard to imagine we get definitely moisture throughout the, through like 300 millibars, so.
Mhm.
I would, if I had issued an advisory right now, then I would probably lean also towards, winter weather advisory.
Okay.
For
Yeah.
Probably maybe CR, depending on, is of the warm upper layer. but
Okay.
CR probably
Gotcha.
5 inches.
Okay, and if anyone's not familiar, ZR is the term for freezing rain that we use in the grids. So, because this could be any potential precip type. So, but we're already mentioning, that warm layer potentially. We saw that on the soundings. We're warm advecting in the mid levels. We're cold advecting at the surface, but it's uncertain about where we see that clash. So, great points. Okay. It is, yeah, I guess we've gone 24 hours. Congrats, you slept, you made it through your first day, you're back, you got some coffee, you load up your 300 millibar. That's what you got. What did our trough do? It deepened, yeah. QG theory works, we've solved it, we can all go home. Our trough has deepened a little bit, it's gotten a little more intense. That jet streak has started to kind of wrap around the bottom there. It's moving southeastward. Notice the strong flow aloft kind of coming into Oklahoma. So remember our jet streak model, right? Our 4-quadrant. Where is Oklahoma in that right now? Left entrance or exit? Exit, great. And that implies synoptic ascent and fairly strong synoptic ascent at that. And you can actually see the omega, the color fill here, and the ageostrophic wind vectors kind of actually diverging. So you actually have divergence in defluence right now. What happens to air as you lift it? It cools. Yeah, exactly. So I also neglected to mention that you can generate colder air in different levels of the atmosphere by lifting. And you can also do that through other processes like evaporative cooling. When we talked about saturation, there's also just slab lifting an air mass at the surface can actually cool it. So things to keep in mind that we may not have a lot of cold air 48 hours ago, but if we've got a deepening synoptic system, we can change that pretty quickly. So any other features of note real quick on 300 millibars? Yeah. Okay, yeah. So this is 300 millibars, but you can start to see some influence of that. So you're talking about some of the climatology of the warm nose. It may be a little bit weaker. So that's a good point too. That can really influence your precipitation type. So think about that wind direction and where you're moving that air from. Really good point. Okay, we'll keep going down to 500 millibars. Again, same kind of story. You've got a much stronger trough. Overall, would you say that this is, how would you categorize the lift over Oklahoma right now? Strong, weak, moderate? Okay, so we're getting some more strong to moderate lift. Again, so we're starting to get that synoptic ascent moving in. Looking upstream, so part of this trough, that's -26, that's -30 Celsius. Hint, that can also tell you what type of year or what time of year this event is occurring. So because we're blocking all that information out. So just be thinking about different things about that. But again, the gist of this is that you have a really intensifying synoptic system that's moving through. So you're producing a lot of moderate to strong lift over parts of Oklahoma. Remember where we talked about our preferred area of cyclogenesis is in the country? It's right in this area. So you can end up getting strong synoptic lift over the Southern Rockies. You can get a lee low that develops there. Strong low pressure at the surface can help drag some of that cold air further north. It can also drag some warm, moist air further north. can help increase a warm nose. It can also help decrease a warm nose. I'm giving you conflicting information because I want you to think about it. And I'm not going to tell you the answer. Okay, 700 millibars. Moisture, I just heard someone say it, it's changed a little bit. We're still not super saturated, higher relative humidities over Oklahoma, but it's getting closer, right? Kind of tucked underneath the upper low, which I guess I should mention that 700 millibars, it's now a closed low. So remember, it was just a little trough kind of back up over here. So we've really intensified. We actually have a coherent low at 700 millibars now. What do you notice about the temperatures? Those are the little dash lines there. Yeah, we're getting colder. Yeah. So this is 700. So this is about 3 kilometers above the ground here in Norman. So we're starting to generate some colder air, even though that we were pretty warm and we were warm inducting. We've also got some other hints of some even colder air to the northwest. There's a strong front kind of coming through right here in northern Mexico. The gradient's a little bit weaker over here, but you still have a decent gradient. So again, if I'm looking at this, you're actually have cold advection down here too. You've got some perpendicular component to the wind going across there. That's the other way that you can deepen a trough or synoptic system is through differential temperature advection. So if you have cold advection beneath a trough, that can lower the heights within the trough, essentially make it more intense. So this synoptic system still appears to be intensifying. So just be thinking about that. 850. Any big differences from the last time? How are we doing temperature-wise over Norman? Little colder, but still warm. Yeah. So we were talking about the warm nose, potentially being a little less intense. That may have occurred. So we've cooled it a little bit, but we've still got some work to do. Now look up over the northern US. How are we doing on the colder air mass up there? Yeah, it's advanced. It's actually deepened a little bit. So we are advecting some colder air from Canada. Notice the northerly winds here. And this is one of the first reflections of the surface low here too. This is actually close to the surface here in parts of Texas where we're in the San Gabriel's, or not San Gabriel's, the Western Mountains, the Davis Mountains out there. So we are actually developing a surface low off the terrain there. So, okay, here's the surface temperatures 24 hours out. There's that freezing line. We still have good moisture down south. Yep, so we got one ingredient, got the lift. Are we working on the cold air? Getting a little better. Yep. We actually have freezing temperatures in the state of Oklahoma, the Northwest Panhandle. Woo, we did it. Thank you, Black Mesa. We did it. Yeah, so we're getting a little colder. You actually have a little area of surface high pressure up there, so it's moving some of that colder air down. Okay, there's the near surface wet bulb temperature. Again, it's a little further south because we're still dry, so you can wet bulb those temperatures down if you get sufficient precip. And then there is the surface low down there. So, all right, I'm giving you your first bit of model guidance. So here's the HRF. This is the mean temperature field. So this is the model initialization. So we can kind of go back and forth. These are the same times. They look decent. It looks relatively good. So here's what it looks like 12 hours from now. And this is still, so this is now, the 12-hour forecast is now 12 hours before the event starts. So, but it's the 24-hour model initialization. What do you guys notice? It is night, yes. How are we doing temperature-wise? It's cooling a little bit. Yep, I heard that. Yes, yes. Okay, on the northern side there that you're talking about? Okay, yeah, so we get a stronger pressure gradient force, so we're helping to drag or get stronger northerly winds in parts of like northwest Oklahoma, east or southwest Kansas, that sort of thing. And that's where our cold air was, right? So we're helping to drag that down. All right, here's the sounding now for Norman. It's still pretty dry. Our surface temperature, about 15 degrees colder though. So what do you notice about the surface winds? They're northerly, yeah. So we've had a front go through. So we were kind of worried, a day or two ago, we might be still warm advecting. That front may not ever get to us. It's actually gotten to us. The winds aloft have also gotten stronger. I'll just point that out. So that's that synoptic influence. We're starting to get the mass response from the big trough out west. So we got our lift. We're starting to get our colder air in. We know we have some moisture, but we still got some work to do at the surface. We're still a little dry. Okay, real quick, Amarillo. Are we behind a dry line anymore? No, yeah, we've really moistened up. It's a little bit colder. There's the Lee cyclone. So we've actually got easterly winds in Amarillo. So the low is probably to the southwest, spinning up there over parts of West Texas. Okay, Dodge City. Ooh, what's that surface temperature? Oh, did someone say it's time to issue the watch? Yeah. 33 at Dodge City. A wet bulb temperature right around 31. So that cold air mass looks like it's maybe moving south. How are we doing moisture wise? Starting to saturate? Yeah, there you go. North Platte. Does that look familiar to some soundings we've looked at today? Yeah, I see some heads nodding. Yeah. All right, it's decision time. Let's start thinking. Yeah, no. Okay. Okay. Yeah, no worries, man. Don't worry. Yeah. Thanks for making the slides. All right, take a couple minutes. If you guys need me to step back through anything too, let me know. I'm gonna start harassing you with questions though. Who's issuing a product? Yeah.
Anybody have Oklahoma City proper and any headline? Winter weather.
Weather advisory? What do you have, Amelia?
Weather advisory.
Okay, so not southern Oklahoma and the southeast part, right?
The southeasternmost area.
Okay,
Without
without your, okay, gotcha. Anybody have anything else? All right, we've canceled school for the entire state of Oklahoma. You have now been elected the president of Oklahoma because all of the kids love you. Yeah. Does anybody have a watch out and are you still waiting to see what you've got?
There's no water.
I'm still waiting for that.
Oh, sorry, yeah. 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 Yeah, sorry, what I meant to say is anybody holding firm, have you not issued anything yet? No? I've scared you all sufficiently? You've not gotten enough phone calls?
Like south.
Okay. 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 Real quick, does anyone want to see any other maps or anything? Yeah. Go ahead. Okay. Okay. Yeah. Surface temps.
And this is during the day.
Yes, that should be. Yeah. That's morning, I'll tell you that. Yeah. Okay, yeah. All right, so Robbie's got a warning for like Northwest Oklahoma, kind of in the area.
We did that.
Okay, all right. Awesome. We are canceling school in Woodward today. That's what we're doing. All right, last chance to see anything else real quick. Got a little bit more data. Okay. All right, it's 12 hours later. Someone called in sick. You got to come back to work. This is a hell of a first week, man. Yeah. 12 hours later, that's what your 300 millibar cyclone looks like. So remember, we talked about this system continuing to intensify synoptically from our QG arguments. And sure enough, that's what it's doing. It's gone from a big broad trough out west to now it's, was positively tilted, and now it's kind of taking on that neutral tilt within there. Notice that strong mid-level jet or upper level jet, sorry, coming in. Look at all the ascent right there. Remember our left exit region of the jet streak? That's right where we are. You can see the agiostrophic divergence there too. And all of that is omega. That is all vertical motion. You are moving the atmosphere up. So, yeah. If anybody's holding their water on winter storm or winter weather products, I salute you. Here's 500. Again, same story. That synoptic system is probably still going to intensify further. And you've got a really strong thermal gradient right here, a strong jet. You've actually got visible defluence now too at 500 millibars. Those wind barbs are literally flaying apart. So you have a void that the atmosphere is trying to fill through vertical motion there. So you have really strong ascent over parts of North Texas, Southern Oklahoma, all that. All right, there's 700 millibars. We were a little worried about moisture. How we looking now? Yeah, we're starting to get some of the better moisture in there. Got a 700 millibar front right there that's just south of Oklahoma. So remember, anytime that we have an intensifying front, we also have that frontogenetical circulation. That's extra mesoscale lift. So might we be dealing with a band of heavy precipitation? Kind of a mesoscale corridor in there that may drop a bunch of precip? Could we? Could we not? All right. There's 850. How we doing temperature-wise over the Norman CWA? We're almost at freezing. Yeah, we're definitely colder. I think last time it was around 6 to 8 Celsius and we're down to 3 to 4 Celsius. So we've cooled off a couple degrees. That's probably that vertical motion. It's also partially advection. So look further north. That cold air mass has really deepened. So now thinking about the other side of this too, what do you notice about the wind vectors here in this part of Oklahoma? Are we cold advecting or are we warm advecting? Warm advecting, exactly. What does warm advection result in? Yep, there you go. You're also getting vertical motion. You're getting additional vertical lift in the mesoscale from that warm advection. So remember the 700 map, you had the higher relative humidity. So you're also getting the synoptic scale ascent from that. You're getting frontogenical ascent from that. And you're also getting warm advection. So, but there's kind of a battle here because you got to be cold enough for winter weather precip. And at 700, we are below freezing over us now. But at 850, we are not. So remember that warm nose. Are you guys thinking about what precipitation types you were forecasting? Because remember, your Your winter weather product type also was related to how much and what type of precipitation you're expecting. Who thinks this is all snow? No, no one?
I think it might be all snow for the western counties.
Okay, for the western counties. All right, that's a good one. Do you think maybe mixed precip further east? Okay, you're thinking ice storm. Okay. Okay, anybody disagree? Anybody have any other thoughts?
Just for clarification, you can't mix and match the ones.
Yeah.
You have, like, ice storm in one part, winter weather by another.
Yeah. Sorry, yeah, you can issue as many types as you want, anywhere you want. I guess we should have clarified that at the beginning, but yeah, whatever you think. Go ahead.
I see the any south freezing temperatures to the southeast of the zero. On here, I'm holding for you.
All right, you're going ice storm warning. If you see, if she sees 0 degrees temperatures at the surface, it's ice storm warning, okay? All right, I like it. I like it. We're decisive forecasters. Very nice. All right, there you go. Is that what you guys expected to see? So remember, we talked about that 850 warm advection in the southeast part of the state. Might that be having an influence at the surface there? Yeah. It might be a little bit difficult to get certain things. Are we feeling more confident about winter weather in a certain part of the area? Northwest? Okay, yeah. And maybe a lot of uncertainty over central and southern Oklahoma, eastern Oklahoma. Yeah. You think it's all rain? Yeah? Yep. Like I said, this could be a bust. I guess we flipped them. That's the actual surface temperatures, but that's the wet bulb, so essentially the same. But you see, there's our surface low down in southeast New Mexico. We're still forming. It's pretty close to the upper low. But we do have northerly winds. So remember, this is 12 hours before the onset of the event. So this can change. And you get a new model run too. I'm extra generous today. You get 2 model runs. So that's the same time as the previous stamp, surface temperature wise. Oops, sorry. That is 6 hours from now. And that's really hard to see. Yeah. My bad. So the blue here, this little cyan, that is 30 degrees Fahrenheit. The middle here, that is 35-ish. So you can roughly use that as a freezing line. Sorry, we didn't think about that. I didn't realize that that was that hard to see. Well, we absolutely should. All right. Are we still thinking like Northwest Oklahoma, maybe the best? Maybe. Are we thinking all rain anywhere?
Yeah, like Ardmore, that's not.
Okay. Okay. And remember, you guys can change your headlines too. If you put something out and you don't like it, you can move it or get rid of it entirely. So if you put something out and then said, nah, I changed my mind, you're going to school, kiddo, you know. Whoa, I gave you another thing. Look at that. A precip type map from a model. Remember what we just talked about though. Our model's very good at precipitation type forecasting. Do they always have all the details all the time? No, but they look pretty. So sometimes they're fun to use. Does that look like what anyone had an idea in their head of? Kinda not. Okay. So kind of along that 44 corridor, maybe thinking. Yeah. All right, well, let's take a look at some soundings. So This is 12 hours still ahead of the event. So that was a preview, 6 hours beyond these, but these are the 12-hour observed soundings. So what do we notice about Norman? Are we a little cooler still? Yeah, we're cooler, but our moisture has gone up too. Do we have that dry layer anymore? No. But, oh, sorry, I moved it. Our wet bulb temperature, so that's that tiny little blue line. You see that in between there, the red and the green? That's our wet bulb temperature. So if we cooled the profile with precipitation, that's how cold it would be. Is that above freezing? Yeah. So that's important for precip type. So we mentioned the warm nose too. We've got a saturated warm nose. It's, 150-ish millibars deep. So if we've got snow above that, are we melting the snow as it falls through there? And it looks like it's about 2 to 3 degrees Celsius above freezing through that layer. We're probably melting all of the snow if we're falling through there. It's probably deep enough. And now we don't have a cold layer at the surface, but we are still cold advecting. We're also warm advecting in that same layer as the warm nose. So we theoretically could be warming that warm nose even further while also potentially cooling the surface. So think about that. What type of precip do we have ongoing at Amarillo right now? Snow, yeah. All right, so somebody's getting winter precip somewhere. We still got northeasterly winds, we're saturated, and it's freezing, or it's snowing. All right, there's Dodge City. Again, probably some snow. We do have a little bit of dryness, so we may be dealing with some dry air that far north. So that's something to think about if we're moving that air in from the north. All right, there's North Platte. Are we getting any precip out of this? Probably not, maybe some drizzle. Yeah, you're a little saturated at the surface, but you don't have a lot of moisture aloft. So you've got dry air now further north. It's colder, but that cold air comes with some issues. So again, we're balancing all of our ingredients. Okay. Feel free to change your products if you want to. Does anyone feel locked in? Feel confident with what you got? Does anyone have no idea what's going to happen?
I mean, I think I know what's gonna happen, but I thought like, is how much smaller, but also based on that, and like, I'm thinking about what you're trying to do rather than think.
That's the yeah, you got to do it for real sometimes, but this is about as close as we can get. Yeah? I was pointing to you. Did you have your hand up before? Okay. Really? Okay, interesting. All right.
You don't make me say the day before.
I'll write it on.
All right, do it. I would love to see it if you've got it. We'll check it at the end. You can flip it up at the end on the notebook and yeah. All right. Any other big changes from anybody's stuff? Yeah.
My winter score like 2 tiers of counts.
Okay. Any particular data that swayed you?
The model,
Okay. Okay.
It's kind of where I had it, it's very light, so I kind of kept the winter weather advisory, but I even trimmed the advisory, like, let the top row of counties that was now,
Okay.
like top row.
Okay. All right.
You can see this, I'm not gonna.
We'll keep that for later. So, all right. We'll have, I think, one more decision point right at the end. But here is now 6 hours in advance. You're still at work. Everyone called off sick. They don't want to deal with it. You're still at work. I hope you like coffee. Yeah, we're breaking our computer. This is awful. Why did I get hired by the Weather Service? They have student labor laws for this. 300 millibars, so we're still in that ascent region. There's still a lot of omega, so we're probably generating precip. We've got a really strong jet streak kind of moving overhead. It's really no different. We now have a closed low at 500 millibars. So that synoptic system is still intensifying. So we've got that really strong thermal gradient. We also have divergence and diffluence right there. Is that a little deformation axis kind of starting to show up there? It's not quite perfect, but there is potentially some shearing right in there, again, implying really strong synoptic ascent. 700 millibars. What's that dirty D word that we don't talk about in Oklahoma? The dry slot. Yeah, look at that. We're getting some dry air that's moving in. So we're getting dry air that is coming off the Mexican high plateau. We're potentially mixing out some of our moisture. But we've still got strong synoptic ascent. We're generating some precip. We do still have frontogenesis ongoing in parts of Southwest Oklahoma, Northwest Texas. 850 temps, 6 hours ahead of time. How we doing? We are removing counties. So, yeah, anybody, you know, we're colder now. We're near freezing, near or just below freezing at 850 over us. What are we thinking for precipitation type in Norman now, central Oklahoma? Ice? Okay, maybe some mixed phase. Snow? Rain or snow? Okay, you think it's rain or snow? Anybody, anything else? All rain, all snow? You give up? A meteor is gonna fall? Okay. I don't have a sounding for that one, unfortunately. All right, there's the surface temperatures. So there is some diurnal variation in this. So remember, we went from a 12-hour to a 6-hour look. So this is midday. So you're probably going to be a little bit warmer than certain times. So I'll give you that. But we do have some cold air still to the west. So remember, Amarillo was snowing. Norman was not quite. We still have moisture to the south, and we are still moving. But look what our northerly winds are blowing into parts of Oklahoma. Is that below freezing? No. So we are cold advecting, but it's not below freezing, the temperatures that we are advecting. So that's something to keep in mind. All rain, all snow, all sleet, all mixed precip. Isn't winter weather forecasting fun?
I still feel confident that the western parts of the city.
Okay.
That's where confidence is the highest.
What swayed you? Everything?
In fact, that during the day, the pure ice is still east of the western county. There's
Okay.
really enough of colder air, moisture. There's gonna be snow in the western part of the city, right? I feel
Okay.
pretty confident.
Okay. All right, you get one more model run because I'm feeling very generous. So this is the current time. Again, remember, this is like that 30, 35 line. There's 30. Oh, never mind. I wasn't feeling generous. You didn't get it. I forgot to put it in. So anyway, here's Lamont. We get a Lamont sounding. It's a great day when we get a Lamont sounding. Look at the temperatures. How we doing at Lamont? You getting any winter precip? It is close. It is close. We're still cold advecting. But we are cold aloft. The warm nose is not as deep, maybe not as strong, but we are not quite freezing at the surface. Yes, that is this guy right here. So that is about 100 miles north of Oklahoma City. Okay. All right, so we're thinking some wet bulbing action. So again, think about what that does to your precip type. Think about where that may be heaviest, where the models had shown that being heaviest, where the mesoscale and synoptic ascent might be the heaviest. That might tell you what you need to know. Yeah. That is 850. Uh-huh. Yep. It's kind of crappy. I think you had stepped out, but we had talked about the dirty dry slot coming up and maybe getting us. Anything else you want to see real quick? Okay. All right. This is your last chance. The event is about to start. Change your forecast one more time, leave it the same. Are you canceling school at OU? Are you canceling Norman Public Schools? You can say yes just for fun, but. Okay, yes, we're closing school.
No.
No, we're not closing school? Boo, say the children. Oh, we had a big X, we had a no. All right, I'm just curious, what is everyone's final take? How many have winter storm warnings? Yeah, anywhere. Yep. Okay, where are most of your winter storm warnings? Just shout them out. West, okay, southwest, all right, okay. Okay, between 44 and 40. Okay, all right, so it sounds like generally northwest to west to southwest-ish, so the western quadrant of Oklahoma. How many have ice storm warnings? Okay, a couple ice storm warnings. Where you guys have those? Central, okay. All right. Okay. Any blizzard warnings? No. Oh, terrible, terrible. It could be. All right, and winter weather advisories. Finally, does everyone have at least one, potentially more? Yep, okay. Where mostly? Okay, Central Oklahoma. Anybody anywhere else?
We have winter weather advisories for the central Oklahoma, excluding the southernmost counties. Central Oklahoma.
Okay. Okay.
And then, yeah, southeast of like, that like what? Like it's a 75, yeah, southeast is 75.
Okay.
Yeah.
Okay, so it sounds like maybe southeastern parts of the state and farther south, we've got no winter weather headlines. Everything kind of the west, northwest, southwest is winter storm warning, some ice storm and some winter weather advisory over parts of central Oklahoma. So all in all, it sounds like you guys are actually kind of all in agreement with minor variations. So yeah, interesting. This is what happened.
Oh, what?
You are correct. That was yesterday. Yep. That was yesterday. That was the storm evolution of yesterday. So how many people had suspected that that was what we were doing? Yeah. Yep. Yep. Yep.
I thought it was either that or.
Okay. Yeah, that was a good one. Yeah, Amelia. That was it. Well, kudos to you for paying attention to the current weather. Yeah.
So, this is out of curiosity, what was the limiting factor in the part of the state?
Um,
Is it,
part of it looked to me to be ascent, and you started to get a lot of dry air. So the source region for the dry or the cold air was pretty dry. So you kind of started to eat into the precip potential on the northwest side. So one thing that really caught my eye was this 700 millibar front. So you had a really strong frontogenic forcing down in this area. That's partly responsible for the banding that we saw down there. Real quick too, any particular reason why that part of southwest Oklahoma may have gotten more snow? The Wichita Mountains, yeah. Yeah, that's about 1,000 feet higher in elevation. And we were looking at the colder temperatures, 850 was below zero out there. So they had sustained precip the whole time, just like us, but we had much more marginal temperatures all throughout the column. We were never quite below freezing. I think my home sensor like kissed freezing at 32 and then for like 10 minutes and then went right back up. So, but we got snow. It was almost entirely snow or rain. It did switch between a couple different precip types pretty quickly last evening, but it was almost all snow or rain. We really had no warm nose to speak of. That's what would have happened if we had been 3 degrees colder. It would have just been all snow and we would have not been here. But yeah, so this is all the event from yesterday. And I know you guys are aware of kind of what's going on with the weather, with falling and all that, and being forecasting and in OWL and all that. But these events are really tricky in Oklahoma, especially when you do not have a source of cold air already in place. The best thing for snow in Oklahoma is to have a big Arctic high over the plains to the north. Because anytime you can deepen that cold layer sufficiently and it's several degrees below freezing, that is how we get snow here. And good snow is when you have warm advection overrunning that, and then as it transitions to colder, you get the deformation and the stronger synoptic ascent on the backside. That is how we get our big snowstorms here. And one way to look for that, the low position, the 700 millibar low right along the Red River, that loves to get us. But we have to have the cold air with it, and it's really hard to get those two. That's why snow is so rare here in terms of getting actual meaningful snow. So that's all we got. Did you guys have fun? Yeah. Yeah. That is a great question. Go talk to the NWS Norman guys, because I imagine the last couple days have been excruciatingly fun for them. It is really hard precip type wise here. And that's why I joke that our preferred precip type is sleep, because we're right in that transition zone. We have warm advection and we have cold advection. Anytime you're mixing those two air masses, you may get a warm nose, you may get a shallow cold layer, you may get neither, or you may get both. So it's a pain. But yeah, that's all I got. Thanks, guys. That was fun.